So today, another 3 lectures. The first hour, first lecture period, will be a kind of a, these are the things we can do lecture with tunable diode laser absorption. My point trying to be that just combustion is energy broadly that can make use of diode laser sensing in practical applications. Okay, so there'll be no, we had a lot of spectroscopic theory yesterday, no more theory today, really. Just applications in this first hour. And we'll switch and start talking about shockwave applications that relate to chemistry. And the third hour will be on examples of lasers in chemistry. This is a picture of what's called the National Carbon Capture Center, NCCC in Alabama. It's a big thing. It's not a full scale. It's a kind of a prototype coal gasifier. Coal gasifier means you take coal and you're trying to make syngas, hydrogen and CO, and you do that by bringing in the coal and basically combining it with hot water, steam, and it's anytime you involve coal, it can be a hostile environment inside the reactor, which is at high pressure. So the challenge is highly particle-laden flow, high pressures and temperatures, what's going on inside, and monitoring at different stages. I had 2 students go there quite successfully, maybe about 8 or 10 years ago. Okay, I'm going to start with internal combustion engines, measurements of fuel and temperature, and then we're going to deal with some of the problems that are associated with making measurements with hydrocarbons, real hydrocarbons that are blends of fuels. How do we get quantitative absorption coefficients? And we'll come back to hydrogen and temperature, H2O and temperature in this lagging coal gasifier, which is a different kind of gasifier. And finally we'll go to a coal-fired boiler, which has its own challenges. So we're going to look at basically difficult practical situations where laser sensing might be useful. And the main message is that this form of laser diagnostics is practical. You have to live with the line of sight aspect of it, but there's now so many wavelengths available with lasers, and absorption is so well understood that you can engineer devices to work in multiple environments. And of course, these laser systems can be fairly economical. And I've shown you already, I hope, that we can measure species, temperature, pressure, velocity, mass flux, so on. And over time, we've done this, it says 8,000 here, but we've been up to 14,000 now. 50 atmospheres, we've probably been up to 100. Velocity, 15 kilometers per second, multi-phase flows, flows with high emission, scattering, vibration, electrical interference. So there are different challenges in each application, but the science is now well enough understood we can engineer devices. Over the last 15 years, maybe, there have been a lot of applications like aero engines, scramjets, pulse ignition engines, arc jets, gas turbines, shock tunnels, and so on. So as long as there's an infrared active species and a wavelength we can buy with a laser, we're ready to go. So about 10 years ago, we made the measurements in a coal-fired boiler. The challenge of that is that everything's way up off the ground. The measurements are made 100 feet off the ground in some sort of a tower structure that allows access to the optical path. Coal gasifier, that was a challenge 10 years ago. That was a challenge because coal gasifiers, there's a lot of scattering of light, and you're going to see how severe that is. This was at the University of Utah, small scale device. And IC engines, my student, Jason Porter, Colorado School of Mines, now professor. We did this project for Nissan about 12 years ago on a real production engine in Detroit. So here's the idea with IC engines. And this was kind of like analogous to my idea of using diode lasers to probe different parts of the scramjet. I can imagine a suite, they call it a suite of diode lasers, different colors, different wavelengths, propagated by fibers, either to probe the inlet manifold where you might want to worry about EGR, where you might want to worry about fuel. Water is especially important also for some applications. Or you might want to probe the exhaust manifold where you'd be interested in carbon monoxide, NO, other hydrocarbons, and you might want to time resolve the exit flow from the chamber. Inside the chamber, we've done both cross cylinder measurements. Yeah, not at Nissan, we did that at Sandia Livermore. And temperature and water and fuel and EGR were targets. I didn't have an IC engine at Stanford, so we had to take our device over to UC Berkeley across the bay where Professor Dibble had an engine lab. So we built a sensor, got it to work, took it to Berkeley, proved that we could fit it up into an engine before we went on to Sandia. This is there they have a transparent cylinder, so that made it easy to go across the pulled up across of the cylinder as function of time. That was an interesting problem. So when you have high pressure, sometimes the optical properties of the windows change. There are reasons why this happens. So if you subject one side of the window to say 50, 100 atmospheres, the transmission of the light can change. It has so-called birefringence. And depending on the polarization, there's a different propagation of say, vertical and horizontal polarization. Well, we never run into that before. So there's almost always a problem. It's often associated with the windows or the scattering inside. So you eventually find a resolution. Okay, then we went Nissan 2007. That was Detroit. That was a production engine being tested there. And basically, usually we develop the concept, do it on a bench top, maybe test it in a flame, assemble it with fiber optics, take it to a prototype engine, and then eventually we actually went to Japan and did this successfully. Now, in order to do TDLAS, if we were doing a small molecule, we need line strengths. If we know the temperature, we can use the temperature to get the line strength of the species. You pick a wavelength, get the line strength, deal with the line shape. Now we have a different problem. We have a blend, a fuel which is a blend. It's not a neat hydrocarbon, meaning single species. So the absorption spectrum around 3 microns looks about like this. We looked at this yesterday. So this would be regular grade gasoline from a local pump downtown. And take the FTR spectrum, this is what you get. Trouble is, if you go to the next gas station down the street, it looks different. Why? Because the gasoline has many constituents, and therefore it's hard to know what is the spectrum of gasoline. Well, it depends on the gasoline. So that was a challenge. How are we going to make quantitative fuel measurements in an engine? Well, it turns out that at least Nissan, their engine testing lab, they would have gasoline delivered, and the gasoline delivered there, they would tell them a few things. They would tell them the fraction of the alkanes, fraction of the olefins. They tell them 3 things. I'll come to that in a little bit. So they know 3 pieces of information. No, they did not use oxygenated fuels, but we do. So in case of US, we ended up needing 4 things. Fraction of the gasoline that's in 4 classes. So the challenge for us was, is that enough information to pick wavelengths for measuring temperature and species that are kind of universal? So that turned out to be quite a big project that we succeeded. But this is what you have. By the way, absorption cross-section. Look at the units. It's about 40, peak is about 40 meters squared per mole. So you ask yourself the question, what's the cross-section per molecule? And cross-sections for molecules, if you had, say, a course in kinetic theory, you can get a hard sphere cross-section based upon viscosity, say, or thermoconductivity. And if you take a hard sphere approximation and measure the properties of viscosity, you can infer a cross-section of the molecule as close to its physical size. But now we're talking about the cross-section for absorption of light. So rather than kind of a constant number that you might get for viscosity, what you see is the cross-section varies with the wavelength. So it's the optical cross-section. It's the cross-section at a wavelength. But if you take that peak value, 40, divide 40 meters squared, divided by Avogadro's number, you get a number of the order of 10 to the minus 18th centimeter squared per molecule. So that's basically the size it represents to capture a photon of light. So that's a pretty good number. Cross section is that big. So you might, just like oscillator strength, it's sometimes good to think about the size of the cross section per atom or molecule. So we measure this with the FTIR, and we identify, of course, this is the CH stretch region, and we showed yesterday, I guess, the differences you get between different CH stretches, whether it's CH2 or CH3, and they're actually, because there's 3 and minus 6, there's so many modes that they're given names, twists, waggles, rocks, stretches, asymmetric stretches, and so on. Now, another problem with gasoline is that the cross-section varies with temperature. Now, this happens to be a case of premium grade, but downtown. And you can see that if you measure this at different temperatures, ranging from, say, 26 degrees up to 500 centigrade, it changes. Fortunately, I guess, it changes mostly in this one region right here, associated with one of those particular motion groups. And so our plan had been, well, let's identify a wavelength that is more or less temperature insensitive and one that is temperature sensitive. And then we'll try to use the ratio of those to get the temperature, and then either one of them to get the concentration of gasoline. So this is the CH stretch. We know more about that based upon the stuff we talked about yesterday. So we pick one frequency with large dependence, so that's 2970 wave numbers. We pick one with small temperature dependence, that's 2951. And so now we hope that we can build a model that will let us know the cross sections as a function of temperature if we know just enough about the composition of the gasoline, even though it might have hundreds or thousands of molecular components. It's going to be dominated, we can represent them in classes. So that was our strategy, which worked pretty well. So here's an example of two different blends of premium grade gasoline, one with 6% aromatics and one with 39%. What do we see? One of the aromatics has less smaller cross sections. So the structure of that ring means that those CH stretches are contribute less to this shape. So the shape's about the same. So in fact, if you know where to look, you would realize it turns out that this is the short wavelength, long, high frequency bump right here. So the aromatics don't show up very much in the 3 micron region. But we can tell from the peak height here, relative peak height, that drop is due to the fact that 40% of the fuel is aromatics, and the aromatics don't absorb at that much, at that wavelength. So we were struggling at that point in time to figure out how do we create a model for the cross sections. When we built a model, I think other people now use it. And the model is the average cross section at a given lambda and T if we know the mole fractions X of J. We know the cross section associated with that species J, we have to sum 1 to 5. So in this case, we used 5 components. 5 components were the normal and the branched paraffins, that's 2. The alkanes and olefins, 3. The aromatics, 4. And the oxygens. In the US, we have oxygenates. They didn't have that. So in the Japanese gasoline, we only had to know 4 things. But the question was, since they're delivered the gas with that information only at their research center in Japan, could we build a sensor that didn't care about anything more than that? So we're approximating gasoline by just 4 major components. That was the idea. So we assumed the oxygenates are ethanol. We knew something about the relationship between normal and iso based upon fuel grade. And so Adam Klingbeil is the student who did this. Looks like he did it around 2007 or so, 15 years ago. And that was the goal. So we built an empirical database. So how do you do that? We would gather up, Adam would gather up a number of paraffins, normal and branch, number of them. He would take the FTR spectrum of each of those samples, and he would establish an average for the paraffins. And he could establish an average for the branched alkanes, and so on. So he would build his model based upon a sample of each of these molecular types. And then so he would get an average value. He would get an average cross-section as a function of wavelength and temperature for each of those classes. And then he would, knowing the mole fractions of each, because that's the information that is delivered to Nissan, we would build a model, having already picked the wavelengths that we were especially interested in. And the idea was we could then represent any sample, any gas, regular, premium, any gas, if we know those 5 mole fractions. That's all we need to know. So we then had to test this model. And so there was a refinery across from San Francisco Bay, Chevron. And they gave us 22, I think it was 21 or 22, I think, samples of gasoline, just kind of random samples of gasoline, in which they would give us only that classification information. They would know more about it, but we asked only for that information so that we could test our model. 21 samples, I guess. I thought it was 22. We hoped that the sample pool was representative of the full range that we would encounter in the real world. And now we're going to go in at our selected wavelengths, nu 1 and nu 2, chosen to be temperature sensitive and temperature insensitive. I think I've told some of the students already, when you do 2-line temperature work, there's a tendency to just find the most sensitive pair. But there's a benefit if you can make one of them temperature insensitive. So that sometimes if you know a little bit about the temperature already, you can use that one wavelength to get the mole fraction. So I like the idea of having one that's sensitive and one that's insensitive when you can do it. All right, this plot simply shows that the model cross-section versus the measured, that's the FTR measured. So we measure the FTR spectrum of each of these things, each of these 21 samples. And we would use the model that we had built from the class average numbers. So he sampled maybe 40 different hydrocarbons to get that model. And he applied the model here, and at the 2 wavelengths, you see it works pretty well. But that was successful. That was long before we really were as knowledgeable as we are now about functional groups and how to think about the structure. It's kind of an empirical approach, but it worked. So there we are. Now we're ready to go. We know the cross sections as functions of temperature at these 2 wavelengths. Now it turns out that this wavelength of 3.3 is a little bit hard to get a laser for. It's kind of in a bad region for diode lasers. It's possible now, but it was not possible when we did this. So we had to create the wavelengths we needed using what's called difference frequency generation. So you take lasers with 2 different frequencies and mix them together and produce a different outcome. It's a little bit like frequency doubling. So you can take a pulse laser, let's say at 1032 nanometers, that's a YAG laser, put it through a crystal, rely on a nonlinear process, and double it. So that's called frequency doubling. So you can create new wavelengths from 1 or 2 lasers of other wavelengths. So that's how in this crystal it's used, it's called piplin, periodically poled lithium niobate, I think. So we had so-called pump laser, and then another pump laser, and a signal laser. You can create from this combination of lasers 2 mid-IR colors, the ones we want, using pump minus the signal, pump minus, so you have 2 different pumps. So you can, and then you have a near IR color left over. So you can create new wavelengths if you can't buy the laser that you want. But this is, the trouble with nonlinear processes is these lasers were really wimpy. I think we got 100 microwatts. Most of the time now with our diode lasers, we'd be looking at 1, 2, 3, 5, 10, 20, 50 milliwatts. But the optical fibers we were going to use in our practical application weren't too long, so it worked. It's interesting how little power you need to do absorption measurements. I don't know if I mentioned, I don't think I mentioned it. The very first UV ring dye laser experiment we did around 1980, I had the first CW ring dye laser, which means frequency doubled, we could produce 300 6 nanometer light. But it was in a building, we couldn't move it, so we, not knowing what we were doing, about 150 feet of optical fiber. It was just kind of a long cable, and out only came a couple of microwatts. But we did the world's first shock tube experiments with that laser. So you can get by if you don't have a lot. If it's not a really bright environment, you can get by with a very small amount of power. So this is a way to get the wavelengths we needed, which were around 3 microns. Now lasers are accessible at a lot more wavelengths. 3 is still a little bit hard, but and also long wavelengths like 15 or 16 is hard. So difference frequency generation is a concept that people can use. And of course, it takes more lasers. This system costs us about $50,000 to make this happen. It's pretty simple to set up, but it was expensive and weak power. Okay, so at this point we have the target wavelengths and a near-infrared wavelength. We wanted to carry around that near-infrared wavelength because we were anticipating making measurements in the inlet manifold where there was vapor and droplet, or liquid film on the windows. So we were very interested also in the absorption that takes place in liquid. All right, so we're ready to go. So the first task we had was, could we measure the temperature of the gas next to the spark plug? So, and this was a team effort. We did the laser part. There was a company partner who built this modified spark plug. Basically, it's a conventional spark plug, except off to the side is a short cavity. So fiber comes down through here, and then there's a little reflector, a little metal reflector, separated by 5 millimeters. So that means a 5 millimeter optical path, 10 millimeter round trip. And it's just a low quality mirror. It's a little metal mirror. The mirror would get dirty, we'd have to polish it back up. But all you need is some light to come back. You don't have to have all the light back. Why? Because we're either going to be scanning over lines, we only have to interrogate the light that comes back, all right? That was the idea, initial idea. And the goal was to measure, I think my slides are mixed up. We had 2 goals. We wanted to measure, my slides are mixed up here. Okay, the first project was to measure temperature and water. And when we looked at the spectroscopy and 5 millimeter path, we realized that the absorption signal was way too small. That's when we went to our first wave mixing, degenerate mixing, doing wavelength modulation. And that was Greg Rieger was one of the students. So we learned how to do wavelength modulation. And that was enough to get success with temperature. Well, we measured water and we measured temperature. Then we went to fuel to do the fuel. Turns out the fuel is really easy. The fuel is so strong, absorbs so strong. I know what's happening. I took out several slides that dealt with the temperature sensor. So they wanted to probe what's happening near the spark plug. And the goal was, could we characterize the cycle by cycle variation in the fuel air ratio and relate that back to cold start emissions? So they're worried about the statistical variation in the exhaust of unburned hydrocarbons and tracing it back to how things are behaving by the spark plug. So now we have, I realized I left out some slides. So we have 2 colors, lambda 1, lambda 2, and so we're seeing now this is a single cycle. So you're seeing the absorption pressure is, okay, absorption's on this side, green and blue, purple, and then red's the pressure. And so you can see that they're actually fairly similar, but there were differences. There's an ignition point. And so the question was, cycle averages, what are the statistics? And they wanted to relate, they had no idea what the cycle, they had no idea. The question was, is it related, can they correlate this? Is their engine designed such that there'd be only small variations in the statistics, and they then adjust their design to give low emissions? So this was a big deal. So they, at the time, I don't know what it is now, they wanted to understand the first 400 engine cycles. So when you first crank up the engine over 400 events, what is the variation in the gasoline mole fraction at this location? So the plot on the right is basically shows the statistics. And what's important is that the width of this region is narrow. So that was a big deal for them. That meant that their design was repetitive. It was a kind of not a wide fluctuation. It was a big deal. So that was a new tool to characterize their injection designs for their fuel loading in the engine. Okay, any questions about that? So I mean, we now have a new project for another engine company which builds racing engines. And they have now very advanced CFD models. And they are worried about very subtle effects in the inlet manifold. There's always some water vapor. And what does that mean? And if there's some water vapor, there's some water droplets. What does that mean? So they're worried about what's going into the engine every cycle and what's coming out as they do their CFD. Among other things, we found that there's also, in these racing engines, there's kind of a boost intake. And the pressurized region oscillates in pressure. So we found oscillations in the droplet loading, which then the droplets have to evaporate. So what's going into the engine is changing with time in a way that they didn't actually appreciate. So that was good. So that company is very happy with what we're able to show. Now we're engaged in trying to measure in a real six-cylinder engine in the exhaust. So the idea being that they really have no way to validate their CFD models for these details. What's going in as a function of time, and so on. All right. Coal gasifier. We went to University of Utah, got a grant from the Department of Energy. Coal gasification was a bigger deal 10 to 15 years ago. And the idea is to use that energy resource to produce syngas. And of course, it's a nasty environment. And so for the most part, there were four regions in this. This is a schematic of a reactor. I'll show you another one in a minute. And this is inside the reactor and kind of at the exit of the reactor. And before and after the cleanup of the syngas, they removed some stuff. So we wanted to use diode laser sensing there. What they would have the ability to extract samples and then do a GC analysis. So you have the ability, those analyses might take 30 minutes. So they would have the ability to see, well, how's our gasifier working as a function of the reactor conditions, temperature, pressure, and your loading. You know, the way they load the coal is kind of amazing. Sometimes it kind of goes in big burps. It's not just kind of smooth gaseous flow, it's intermittent. And of course, the goal eventually would be to use the syngas in a gas turbine. So this was kind of a schematic of what you're trying to do. Could we build a sensor that provided control signals to optimize the gasifier output and what goes into the gas turbine, the input, for energy efficiency and best performance? They're especially interested in the gas temperature and the energy, so they really want to know the energy content of the syngas. One of the problems is the syngas includes hydrogen. We don't have a good way to measure molecular hydrogen. People come to us and say, how do we measure molecular hydrogen? It's a problem. So we usually have to do it indirectly. You know, if you know the CH ratio, this is our trick. If you know the CH ratio and you measure all the carbons, you can deduce the hydrogen because all the remaining hydrogen atoms will be in hydrogen molecules. So hydrogen is a problem. We're working on it now, some new ideas. It would be great to have that capability. Some of these systems are added oxygen. So the species that you mostly care about to characterize the energy content would be CO. We know how to do that one. At that time, we were probably using 2.3 microns, which you would know is the first overtone. 4.6 is the fundamental, which is 100 times stronger. But there's enough CO we can do this. So we can use CO 2.3 or 4.6, methane at 3 microns. Now, methane, as the molecules get bigger, the spectra get broader, and they're no longer discrete. Methane has a discrete spectrum. Acetylene has a discrete spectrum. Ethane has a discrete spectrum. But just about when you get up to like 3 carbon atoms or more, you kind of lose the ability to look at individual features. And we get hydrogen by gas balance, okay. We made measurements at 4 measurement locations. Now, usually, it may be that you can't be in the same room with this device. It's a pressurized reactive vessel, so there's fiber optics everywhere. Okay, this is the one at Utah. So they would bring the coal in at the top, and it would come down, and coal would be heated, and it would start slagging. That means you have liquid coal running down the walls across your windows. So that turns out to be the big problem. How do you keep the windows clean? Windows are almost always the biggest problem in these applications. So coal comes in, oxygen comes in, and they burn it, and then they extract it. Stuff comes out here, and it goes up, and we have some sensor here. We had a sensor up here where we had big problems with the window, keeping it clean. Sensors down here where it's coal's pretty much burned up, and then over here where we're just basically this is the output, syngas output. That's the easy one. And so this is a place that they had only thermocouples, pressure gauges, and GC sample. That's all they had. And you'd like to know what's the energy content of the fuel. So we tried to take our measurements and convert that to energy content. 50 to 200 psig, not really high pressure, but high enough to cause trouble. So what happens when you go to high pressures? The water lines, which are everywhere, get broadened, and it was very hard to isolate individual transitions. So you have to kind of represent the superposition of those lines and still find temperature-sensitive ratios. Okay, so we're measuring water, temperature, CO, CO2, methane, and inferring the hydrogen. From that, energy content, energy flux. So the problem with these high pressures is illustrated here. So if we had 1 atmosphere, 25% water in air, 1600 Kelvin, 15 centimeters, this absorbance, that means absorbance is 0.2, so the absorption is of that order. So now if we do this at 1 atmosphere, we have nice isolated features. 15 atmospheres, now we got trouble. There's no place where the signal goes to 0. There's no place the signal goes to 0, so it's harder to interpret I over I0. And you have to sum up your void profiles and deal with it. The biggest problem, though, is that the particulates in the syngas. So as you're sending the laser beam through this cloud of particles, cold particles, the light is extinguished, and not very much light comes out. So the question, and that's where we again got into this might be the first time we did 1F normalization. So this WMS 2F over 1F. Why? Because remember, 2F over 1F cancels out the intensity dependence. So the question was, if you bring in I0, what fraction of the light comes out? And it turns out that we encountered high extinction. I think I've got this slide here. Yeah. So we measured the laser transmission in percent versus the pressure in the reactor. And by the time we got down to 150 psi, 10 atmospheres, we were down to 0.1% transmission. So in other words, only 0.1% of the light's coming out. But that can be enough, as long as you can modulate the laser and discern the molecular contribution. That was a big deal, solving that problem. So basically, the particulate loading went up fast with pressure. I think the highest we've been is maybe 50 atmospheres. But really, in the end, it boils down to just how much extinction do you get. Yeah, that was our first successful application of 2F over 1F. Here's the two students working away on ladders. So this University of Utah is big on coal. They have a big coal research center there. I don't know what the power level of this reactor is. You can get a size of the scale there. Of course, it's really inside. There's all sorts of ceramic brick because they got to heat this thing up to 1,600 degrees or 1,700 degrees to get the coal to melt. Fiber optic. I think the control room was about 100 feet off to the side in a room upstairs. And once they they start heating it up. It might take a day to heat it up because there's a lot of mass. And once they start heating up and they run a test, you can't go out there. So everything has to hold up for about a day. So this is measured temperature. So this is water line ratios, measure temperature at 200 psig with only a little bit of light coming out and with all this broadening going on. And runs would go for many hours, so this is just an example of 400 seconds. And you see fluctuations. Of course, first thing you assume is, well, something wrong with my sensor, it's got some noise problem. But it's actually quite possible, that, in fact likely, that these are real temperature fluctuations that are occurring in devices like this. I guess we got down to light transmission as low as 0.02%. And I don't remember how much power we had going into the fiber, but it was a few milliwatts probably. So we finally decided that these temperature fluctuations were actually real and that they were not our sensor, that there were actually fluctuations going on and related to the way they feed the coal. Now this was, so we're now getting close to, we want to know what's actually coming out, how much syngas did they produce. This is before they clean it up, and how much energy content does this have. So what they really want to know is like how much CO, how much hydrogen do you have, how much energy do you have going into what would have been the gas turbine. They had the ability to extract some samples with the GC, which is how they'd always done it before. So the virtue of the TDL is truly continuous. But they weren't happy until we showed them that we got basically the same answer as the GC. They're chemical engineers, so they're comfortable with GCs. CO2 mole fraction, same thing. What do? They have to vary the proportion of coal and oxygen. That's what they do. They have the temperature, the pressure, and they vary the feed rates in order to get at their desired output. Okay, the GC data, once they extracted it, took 4 minutes, so there's kind of a time shift. Our stuff is in real time, their stuff is always delayed by about 4 minutes. Methane was important to them, and we weren't sure we were going to be able to measure this, but we have to know the methane spectrum at these conditions and so on. So again, we found good agreement with the GC. That was a very successful campaign. It took about 2 years. Water. Okay, so at that point we declared victory. It works. Go back to our DOE sponsors and get ready to go to an industrial scale. Now, that's a lot bigger. I don't know how tall that thing is. Big, and yet it is not actually a full-scale plant. It's kind of like a prototype plant, small. And now the challenge is, can we take this technology and take it to this place, which is no longer on the floor of a room in the building. You're up in the air. There's some sort of instrumentation shelter up there, 100 feet in the air or so. And then, because this is the government, extreme safety rules. This thing is pressurized, I don't remember, it might have been 50 atmospheres. Pressurized, it's heated, you're up in the air, pipes are hanging in structures. And they say, you're going to put windows in our duct? No, you're not. Okay, so we're finally convinced we can put windows. Well, what if there's a leak? Okay, so they end up creating this incredibly double safety scheme so that if anything went wrong with our sensor, it wouldn't shut down the entire plant. Lots of optical fibers. So they put in coal. And it goes through several sections. Finally gets to the place. This thing is so big, actually this sensor was probably about 90 feet away from the last processing element of the system. The nominal conditions were 15 atmospheres, 600 Kelvin. Those are the expected conditions that we were going to have to measure. So the challenge in this case was to measure the syngas composition 99 feet downstream of the particulate control device. So everything's big. And that duct, I can't remember how big that duct is that we had to measure across. Maybe 12 inches. But that structure with the laser receivers and transmitters was 12 or 14 feet long. So they had multiple valves and safety procedures. In this case, we only got 0.01% transmission of light. Still enough. So one big advantage of, I'll call it ScanDA. Big advantage of ScanDA is you can deal with extreme background extinction as long as it's flat the wavelength. Okay, here's a picture of this thing. You have these multiple valves and shutdown procedures on both sides. I think once you convince them that it's safe, you can make it much more compact. Much more compact. We had the same problem when we take our system to NASA Ames, which we've been doing for 15 years. Those technicians are they don't want you to do anything to their arc jet, water-cooled arc jet. So they're now comfortable that we can drill little holes and not harm their performance. We had to have redundant shut-off valves and redundant windows. What if this one fails? We got another one. The science was kind of easy, and the engineering was tough. Here's a picture. This was a horizontal pipe. You can see now, this is a horizontal pipe that we're trying to probe. There's the structure. It's kind of all the way across here. Now, the good news is they had engineers that helped really design this stuff. We had to help them design it, but they really then built the parts and put it together. So here we got the little teeny fibers and diode lasers, all to probe across that duct. Now, these things are big, so the startup is like days. So they'll bring it up to temperature with propane. They'll heat this thing up. Looks like it took about 40 hours to heat this thing up. There's a mole fraction of water, probably. Propulsion. So basically, they heat it up and then they start putting in the coal. When they put in the coal, it looks like their signal went crazy. What's going on? What's wrong? What's wrong? What's wrong? Well, it turns out it was real. The way they put the coal in is in bursts. It's real. They'd never seen this before. So we blew this thing up, and once we blew it up, we realized, well, it's repetitive. It's real. It's not just random noise. And then, of course, we're looking at variations between 6% and 10%. Isn't it interesting? We were able to resolve such a small amount of water, and the variations are really not that big over hours. So we began to have confidence in our methods. And it was related to just how they pulse the coal into this device. Then finally, they're up to condition, and they start gasifying. At 54 hours, they shut it down, so we just see that the signal reveal all of this. So let's see. Oh, students were there for about 4 or 5 days. I think two students. And it was working, so they came home and left it running And it ran for quite a few days, a month, I think. There are a couple of little bursts, signals here that turned out when they would, they stopped the operation for something. So this was, what have I shown you? This diode laser sensing can be practical, even in a very hostile environment. Of course, it's a lot of work, so why would you do it? Well, you do it because there's no other way to get that information. It might be important to characterize this national facility. Light transmission was stable. That meant our windows and our optics held up good. No degradation of windows or laser performance. So this was, they really cared about the amount of water because they didn't have a way to measure the water content. They had to extract some sample and then go analyze it. And they only would do that intermittently, but they still wanted us to compare. So we're measuring, oops, that's like not too far. Okay. They would do this intermittently, and they just wanted to know if we got the same answer. So the nice thing about our diode laser sensing, it just hums along in real time. We could use these fluctuations that we saw in water to correlate with their temperature. They were measuring with thermocouple. So basically, everything worked, and they began to have a better understanding of the transient nature, the fluctuating nature of their system. Okay, I had another big project. This was Xing Zhao, professor at Tsinghua. And her measurement was somewhere up in the air about 100 feet. So it's amazing how these students, they work in the lab for a couple of years, put this thing together, take it on the road, and make it work. It almost always takes 2 trips. Well, it usually takes 2 trips. Sometimes we can only have 1 trip, but usually something unexpected goes wrong on the first trip, and you have to go fix it. But we've never failed. Every campaign has been successful. So coal-fired power plant, they were especially interested in the CO and the NO emissions. So they burn coal, pulverize it, put it in, and they control the NO emissions with injection of urea. So urea is a compound that has NH2 molecules in it, and the NH2 reacts with reacts to form OH. I said that right. It has NH2 compounds in it, and the reaction takes place. It's called selective catalytic reduction. Thermal-Enox is sometimes called. Anyway, it only works in a narrow temperature range of about 1300 Kelvin, and that's the way that they control the NO emissions. So there's always a question about, and you put it in some spray bars. There's always a question about how well is it working. The other question is always, are you using more air in the power plant than you need to control the CO? So they inject enough oxygen to control the CO level, but they don't want to have too much oxygen or too little. Too little is a safety hazard. So they really were concerned about CO and NO, and we wanted to measure this at a certain location where they actually had already some windows. So they'd had a previous contract with somebody else. I think SNCR stands for selective non-catalytic reduction. So we always have to worry about water interference. Here's the problem. So we get a contract, we're going to measure CO. These are the nominal temperature, pressure conditions. What wavelength should you use? So you always say, well, I'm doing CO. This was long enough ago, we were using 2.3 microns. So you calculate the spectrum, or you get it from Hi-Chem. You have to calculate it at the relevant temperature. Hi-Chem database will be at 296 Kelvin. So you have to convert it to your temperature. You calculate the spectrum and you look for windows. So here's a couple windows for CO. And you now know what this means. RF10, so it's an R branch transition originating from J double prime of 10 in a 0 to 1 vibrational transition. No, excuse me, 0 to 2. First overtime. So we pick out a couple of candidates. Have to do the same thing for nitric oxide. Nitric oxide is harder because there's not a whole lot of nitric oxide. So now we're at 5 microns. So there's a few windows. So a lot of the work goes into find a window, prove it in the laboratory, because the positions of these lines may not be known precisely. So you have to prove it in the laboratory. And you're ready to go. We found 2 candidate lines, not many. And we have to worry about the particulate, but we have this 2F over 1F approach now. It turns out that this was a research section of this coal-burning power plant. There were actually 3 boilers, and they had come together in one common stack, I think. It was about a 3-meter path that we were using. 5.2 microns for NO, that's QC stands for quantum cascade. 2.3 microns first overtone for CO. Dusty environment, scattering losses, but we only lost about half of the light, so that was good. Now let's see that. I think that's the student and the sensor there in the middle. These are big things, and the gas flow is kind of going vertically up here, up and then coming back down. She told us that they were on some sort of grading structure where we put our equipment. It was 100 degrees most of the time, and she had the special shoes because the grading was so high, it was melt the bottom of her shoes. And we have to put all of the sensitive stuff in an air-conditioned box, so then fibers cannot go across and come back. But it worked. And this was the work on the CO. So what they really want to do is measure the CO, because they want it to be, you'd like it to be low, but you can't afford to put in too much oxygen to drive it down, and the efficiency of the power plant goes up. So anyway, we showed that we could measure this as a function of time. They could use this to characterize the method they're using for adding air. So you can see right here, when you have excess air, you can drive the CO down. So we're detecting about 10 parts per million, 8, 9, 10 parts per million. Of course, the timescales are so long, you can do some averaging if you need to. Correlates with the excess air as expected. Sensitive detection. The way they would have measured the CO would be at the exit of the stack, which is, I don't know, 30 seconds of way downstream in the system. So, and then you'd have to, anyway, this CEM stands for continuous emission monitoring. That's a standard way for these places to characterize the emissions of their power plants. And we did NO, and now what they're doing is they're varying the amount of the urea that's being added to this flow and trying to see how efficient it is. So this is the NO concentration. Looks like the lowest one we have is, this is the urea over here in gallons per hour. So the black, this must be the NO here. So when you have a high amount of urea, you have a low amount of, but how much? How efficient is it? And so they needed this real-time NO detection to do that. Again, it avoids having to try to do this at the exit of the stack, which is, I think, something like 30 seconds of flow time away. Oh, okay. They actually had 3 boilers that were going into one stack, and they were running CEM at the top of the stack. So we could put this on individual boilers, and we told them we could do this on individual boilers. Okay, so I think I'm almost right on time. So what I would try to show you, to kind of get away from the theory for a day or for an hour, the TDL sensing it can be portable, practical. You can measure a lot of different things. Each system is a different challenge. It's usually, once you pick the positions of the lines and you know the strengths of the lines, the science is pretty much done. Now you get to decide, is it scan DA, is it 2F over 1F, and what is your window design? That's usually the biggest problems. I think there's a lot of potential for this in control of combustors. It could be used in compliance monitoring, complete emissions, so somebody's working on it, and you could do something like this. I wrote this slide a few years ago, but looking at the future, extension to mid-IR, well, we've already now done this. Mid-IR is now common. The UV is not yet common. There's always new species. I could have added these HC in here and other things. So there should be some opportunity with biofuels, natural gas, and some new energy. So there's now a big push for how do you produce hydrogen and how do you transform natural gas into hydrogen. Well, there's going to be some opportunities for characterizing that process. Okay, so I'm done. I'll take some questions. We'll take a 5-10 minute break or so, and then we'll start talking about shock tubes. Yeah, question.
As far as the problems with the windows, and specifically this glass cylinder at San Diego, you were saying you had problems with shining the light through the window with such a difference in pressure. Yeah. What were some of the tricks that you had to use to get around?
Usually you control the polarization. So, for example, if this is a window in the shock tube, we learned that you actually have to buy certain quality windows that have less than that. But it's basically, the big problem is it's called birefringence. And so the transmission properties of the window, which might be a sapphire crystal, depend upon the polarization angle. And if you don't know that or don't think about it, so what does that do? It causes, when the pressure comes up, it changes the transmission. So due to that effect, you have to distinguish that from the molecular absorption. That reminds me of a project we had. Anyone here from Wisconsin? Okay. So my student, Scott Sanders, I don't know if you know who he is. We had a project and we were measuring the transmission of light through a shock tube with two windows. And you know, you measure I0 and then we fill the shock tube and we fire it. And when the shock wave went by, more light came out. So this is a puzzle. You expect something to happen to reduce the transmission. It went up. And eventually we tracked this to the fact that, well, this was a situation where we formed very thin films of water on the window. So, you know, light comes into a window, some light's reflected. Depends on the properties of. So basically, it's kind of like a air coating of a window. Very thin film of something can actually increase. We eventually sorted that out. But the more common problem for high pressures is this birefringence. So polarization control would be the first thing we would do. And maybe you buy materials that are less subject to this effect. We never noticed it until we got up like 50 atmospheres. We did experiments, the highest experiments we've done are probably about 400 atmospheres. So things just get worse when you go up in pressure. It gets harder and harder. Yeah?
So building on that, did you ever have problems of solid deposition on the windows?
Yes.
That can
yes.
be.
Yes.
And did you have like clever ways to add something to keep your windows clean? Did you have?
Okay, so that it just depends on the situation. Sometimes you have to have like a thin curtain of air. You know, the main thing is you don't want to distort the path length that you need to know. Okay. So it.
And it also is true that if you have a sheet of air that you are including that also in the measurement break.
Yeah.
You have an
Yeah. So window problems are often the limiting problem. So when we had coal slagging, we just had to keep that stuff off the window, or we could live with some of it as long as some light goes through. So the problem we run into this, we have to be careful. We're doing some work right now with sooting formation. That's the problem on the windows. If you're doing scan DA, you can live with that. Windows getting gradually dirty or blocky, because you're modulating rapidly across the line, and you don't care if I0 is going up and down, as long because you're only measuring I over I0. The I0 is measuring, okay. Scan DA solves that problem. But if you're at high pressures, you can't recover the baseline. So each problem is a little bit different, but it's always problems like that are the limiting factor. Interference absorption, interference emission. Sometimes we have beam steering problems. It's kind of, you just have to engineer it out of the problem.
Did you ever have to increase the laser power in any case because of these kind of issues?
Yeah, well, we tried. So when we ran into the problem where we were only transmitting 0.1% of the light, we started to investigate an amplifier to boost the power. But by the time we got that amplifier working, we figured out we could live with 0.1% of the light. If you start with, 10, 20, 30 milliwatts, you're probably still okay. I told you that first experiment we ever did was 100 microwatts. And that was microsecond time resolution too. If you calculate how many photons that is per second, that's still a lot of photons. If you've got a photon quantum detector, sensitive to individual photons, you can still do this. Another question?
Yeah, how do you compare the results that you got from the exhaust of the syngas at Utah to the GC? I mean, did you collect every certain time?
So the GC always, it was a long time. They could grab a sample, go to their GC, minutes later, get a number. So but if we do this at continuous function of time, we always found agreement. So, chemical engineers are more comfortable with using their sampling in GC, but we can measure real-time fluctuations. So what we have to do is we have to assemble a practical system that is robust and economical enough to replace the GC. It could happen. Yeah.
You mentioned the measurement the power plant does usually at the top of the exhaust stack. How is that?
Say that again.
The power plant measurement at the top of the exhaust stack is 30 seconds downstream.
Okay, so
Is that usually just done with an FTIR or something? Or
they use different techniques. So let's see. I've never actually done it. But CEM stands for Continuous Emissions Monitoring. That's the standard that they apply to that industry. They may grab samples from there and bring it down to instrument shack down on the ground. So there, if they were sampling for, and then you always have to worry, does the chemistry change inside the sampling? These are stable species, so you're probably okay, but that's always another thing. So you notice that these sampling methods can't measure radical species. Okay. So, but fortunately, most of the things we're talking about right now are stable species. So if you come down for NO, it would probably be a chemiluminescent analyzer. CO2 would be by non-dispersive infrared box you buy it. So I think they bring it down by a sample line, put it into their, and they'll probably have an instrument shack somewhere on there, because that's what they do, because they're regulated. They're regulated. They probably, I don't know what else they have to measure with. Certainly NO and CO, and maybe some unburned hydrocarbons. Go ahead.
For the Utah experiment, you've shown windows on two sides, but you're doing a number of measurements like CO, CH4.
Yeah.
So are all of those lasers going through the same
Yes.
path or
Yeah. Okay. Usually, yeah. Now that was the case. Okay. Inside the reactor, I think we were probably focusing only on water. So once going across the reactor, we're probably mostly just water. Once we got down outside for this, looking for the syngas that was produced, I think we had. There's free space optics and fiber optics. So sometimes we would have the lasers just kind of pointing through the window. Other times we would have them propagated by fiber. But they certainly go through the same path. Sometimes through the same fiber. But if it's free space, they're just parallel paths going through the windows. We have, let's say, the CO laser and CO2 laser, and both going through the window.
So you put like a horizontal window, like
Yeah, usually horizontal, but
side by side.
sometimes vertical. So we've done experiments where we'll put multiple lights through the same fiber, or we'll have separate fibers. Yes?
Yeah. Also, was there a reference detector to collect the I0, the reference lead, while collecting the while measuring the exhaust gases?
If it's done at low enough pressure, we would use scan DA, so we always get I0 by scanning on and off the line. That's the safest method. If it's at higher enough pressure that we can't get an I0, then that's always a bit of a challenge. So there's different tricks that we play. So We use a you're going to see in the shock tube studies that I'm going to show you, we tend to use a reference detector, but in an ideal world, the laser output is rock solid. It doesn't vary with time. Usually the reference detector is to correct the fluctuations in the laser. If the laser is steady, solid, you sometimes don't need a reference detector. But you might, and just might do scan DA. So you're pointing a laser through a cloud, and you're scanning rapidly across the line. And what your detector sees is I0 going down to I. And that's all you care about. That's the power of that concept. But it is a problem when you go to high pressures. Any other questions? Good, appreciate the questions. One more.
Yeah, just, when you're developing such ideas like scan, modulated scan, spectroscopy, like, is it like it was always in your, the way you measure things, or is it something you developed over time and you can share? How do you end up developing such new ways of measuring?
Ideas come spontaneously. You know, you have a problem, and how can I solve this problem? And, oh, try this. And, so if you're the pioneer, if it's already been done, you read the paper and, oh, that's how they did it. And that's a more common situation. You know, you're learning and you're trying to come up to speed with what some other group has done, and then you have your own problem, and you'll decide how you solve your difficulties. But when I started in laser absorption, I had the first scannable infrared laser, diode laser. It was around 1977. They had been classified and used for uranium separation. So these lasers existed, but only at Los Alamos. I got the first one. Now, of course, they're not classified. And so all of a sudden, the question of how do we use this thing? And I had this idea that I wanted to study spectra of high temperature gases. So I wanted to do it in the shock tube, where I only have hundreds of microseconds. So I thought, well, the spectroscopists who were using these devices would scan very slowly and then use a chopper, if you know, guys know what this means. So the spectroscopists will scan signals slowly, chop it at, say, 100 hertz, and do some signal averaging. So it was kind of like a new idea. Can we scan a laser fast? And so it turns out that was amazingly easy. I learned how to do it, and I was no electrical engineer. So that was a breakthrough. Now now everybody does this, and they've used different names. But so you can do scanned absorption. And therefore, as I'll show you in the next lecture, we could look at the shape of lines in shock-heated gases, where we may only have tens or hundreds of microseconds. I've always been really interested in shapes of lines. You know, most of the people who use pulse lasers don't do this. They have other methods. But for getting pressure, so one you might ask, well, what are some challenges? What are some needs? There's a continuing need for how do you measure pressure at a point in hypersonic compressible flow? That's the tough one. I'm still working on that one. Any other questions? We'll take a 10-minute break or so. Okay, round two. I know we probably lost some people here. That's okay. So if people want to leave at any time, it's okay with me. But this is my strongest interests are marrying shock tubes and lasers. So we have 5 shock tubes at Stanford. I keep accumulating shock tubes. I don't know how many people work with shock tubes, but usually it's a constant area duct about 100 diameters long, separated into two chambers, low pressure and high pressure. Low pressure on the right is the test gas. High pressure on the left is the driver gas. Breaks the diaphragm, or if the diaphragm, you open a valve. The high pressure gas wants to go, forms a shock wave in about 10 diameters and propagates down the tube at nearly constant speed, and then reflects from the end wall. So that's how it works. And this is, let's see, this is a picture of, Okay, we have names for all my 5 shock tubes. This is a picture of the one that's about, this was, anybody here from RPI? Well, I have a professor, a student who were there, Matt Olslager, assembled this one. So we sometimes call it the Olslager tube. So the driver's on the left here, and this is the driven section. So the driven section is always longer. This was now the business end here. This is the diagnostics end. I should have brought a new picture. We now have this set up with just lasers and optics. It just looks like a very dense packing. We gradually learned how to measure up to about 5 species at a time. Little optics going everywhere. So this was kind of when we were first setting it up. I want to talk about how shock tubes work, and then we'll talk about vibration, relaxation, ignition, and then I always have some new ideas on things we're trying to make shock tubes better. And then I've got a new idea we're starting to explore on using shock waves to reform natural gas to hydrogen. And then we've got some things that using the shock tube to measure flame speeds. I think those last 2 things I think are pretty unique at Stanford. So we label these regions. So region 1 is the gas we're going to shock. At condition 1, region 4 is the driver's section at high pressure, usually helium, because you want a high sound speed gas. So it's often helium or helium nitrogen mixtures. You want to have a high sound ratio between 4 and 1. Basic concept is you open the valve and it's like a piston. It starts to, the gas comes out, produces a sound wave that steepens into a shock wave in about 10 diameters and then proceeds down the tube. So the nice thing about a shock wave is most of the time we can think of it as a discontinuity of 0 thickness. And if you measure the shock speed, you use compressible gas relationships to get conditions on the downstream side. Okay, so diaphragm breaks in a period of 100 microseconds or maybe a millisecond. Shock wave forms. The gas behind it's been processed by the instant shock wave is in region 2. We call that condition 2. Comes back, that's region 5. So that when the shock wave reflects, it leaves behind a nominally stagnant gas. Nominal, it's not exactly stagnant, but it's nearly stagnant. It is stagnant at the end wall, and we probe there, we probe here, close to the end wall. Why? Because it's stagnant, and the measurement versus time is what we call particle time. We're watching what a group of particles do as function time. And you can produce really high temperature conditions, so we produce temperatures up to right now 14,000 degrees Kelvin. We're studying by this method with quite safe apparatus. Okay, we can work over a wide pressure range. We've done experiments at pressures less than a torr or up to 1,000 atmospheres. I'm going to tell you about the history of shock tubes. So a French person, Paul Vier, a railroad engineer, is the first one he's the one who gets credit for thinking about using shock waves. It's kind of like a water hammer, only in a locomotive, I guess. They had steam and they had pressure waves being generated, and that got his interest. And then along about 1940, and that led to some sort of a device in the laboratory. Then around 1940, people that I know about in the US, Canada, and Great Britain got interested in using shock tubes to study explosions in mine safety, shock-induced explosions, aerodynamics. There was a big wave of interest kind of along about the time of the Second World War to look at phenomena that produce shock waves. To my knowledge, the first use of a shock tube to study chemistry occurred, well, I think it was at Caltech, but some people say it was somewhere else. But it was around 1950, people started realizing, gee, you could use a shock wave. These are chemists. Chemists realized, gee, we could have a step in temperature, which is a convenient way to launch a chemical reaction and study it. So you can imagine if you, time 0, you heat something and you watch it, and you watch the chemistry take place, it's easier to model. It's kind of a simple situation that can be modeled in extracting a chemical reaction rate coefficient. Along about the 1960s, there was a lot of interest in planetary entry and re-entry, which involves high temperatures. And the question is, what kind of chemistry takes place in those flows? How do we model it? How do we study it in the laboratory? And then around early 1970s, I think I was the first university person to use a laser in chemical kinetics and shock theory. But I had a friend at NASA Ames who was a chemist, and he was trying to do something similar. So that was really the birth of bringing lasers to bear on shock tubes for chemistry. But now people use these shock tubes for all sorts of problems. Astrophysics, nuclear explosions, aerodynamics, heat transfer. If you go to the shockwave symposium, there will be people who are using shock waves to break up kidney stones, and using shock tubes to study volcanic eruptions, and just an amazing range of projects. So the thing about the shock tube is it's a device you can put in a laboratory and can produce a wide range of conditions for a short time. That puts a lot of pressure on how do you make measurements. So here's the shock speed relations you would have seen if you had a course of compressible gas dynamics. If you have a shock moving at speed Vs, usually think about it, you fix the shock wave and the gas is coming through, you have the shock temp relations. But if you go all the way through the shock tube, recognizing there's regions, region 4 is the driver, you can derive an equation that shows that the ratio of the pressure, the driver pressure to the driven pressure, as function of the Mach number of the shock wave, shock speed over the speed of sound, and gamma of regions 1 and 4, if these are specified gamma gases. This shows the relationship between the pressure ratio and the Mach number of the wave you produce. And you can use that to show yourself what's possible. Now you go to reflected shock, there's a boundary condition that's 0 at the wall, and you can redo the shock wave equations. And the initial book that most everybody studies is by Gaydon and Hurl, around 1970, 80, British guys. Gaydon was a very famous spectroscopist. Hurl was a guy, I think he worked for Shell. Anyway, the same shock wave relations can be used to generate conditions behind region 5. Okay, this is a way of looking at what you can do. So for example, if you, let's see, where should I look started? Okay. These are plots of pressure ratio versus the Mach number. And typically you're using either a gamma 7/5 gas or a gamma 5/3 gas. It's common to use argon diluent in experiments, gamma 5/3, because there's some advantages. In any case, if you look at the dotted lines are the pressure ratios here. One of them is 5/3. So basically the point is if you have, say, Mach 4, pressure ratio is 100. Got it right? No, it's P5. So you can produce, you augment the pressure by 100, you produce a Mach 4 shock wave. Now you have to ask what pressure ratio P4 for P1 is needed to do that. Now if you look at temperature, this gets interesting. So over here we have the dotted lines are T5. So even, we do a lot of work actually really low Mach numbers. So Mach 4, 10. So Mach 4 gives you 3,000 degrees. Pretty amazing. So if you're a combustion person, you're really looking at 1,500, 2,500. It's really really easy to do this. So of course, if you're doing incident shock, you use T2 instead of T5. So this is how you think about the shockwave process. This is called an XT diagram. So X is the distance along the tube. Here's the diaphragm. Here's the end. It's the driver section and the test section. And this is time. So you imagine that at time 0, the diaphragm breaks instantaneously and it's massless. You imagine. You imagine then that you form a shock wave that moves at a constant speed on this XT diagram and reaches the wall here. The boundary between the test gas and the driver gas is known as the contact surface. So when the diaphragm breaks, the expansion fan moves to the left at the speed of sound. And this is a fan, so the gas is accelerated and comes out along this direction. And so that boundary is called the contact surface. When the shock wave reflects, it goes back at the reflected shock speed, and then it hits this interface. And if there's an acoustic mismatch, if the acoustic impedance isn't matched, as is almost always the case, the shock wave sees that interface and it has to either reflect a wave, or an expansion wave, or reflection. So basically, that wave comes back to the wall, and so you're done. You're done. Unless you are eager to have more time, in which case you can tailor. So if you match the acoustic impedance across this interface, acoustic impedance is roughly density speed of sound. If you match that, then the wave reflection is avoided, and you can extend the test time longer. And we do that when we need to. So here's an experiment that shows kind of what happens. Here's a relative pressure. So we, in times, this is 4 milliseconds. So here's the case where pressure is region 1, here's region 2, here's region 5. It stays pretty constant for about a little over 1 millisecond. And then the pressure goes up because there's a reflection wave here. So your experiment is usually over then. You might say, I want more time, and so there's ways to get more time. There's tricks, we use tricks. There's a way to get 10 milliseconds, and we have another trick that gets us up to 70, 80, 90 milliseconds. But many experiments are really done in less than a millisecond. So if you combine the two tricks that we use at Stanford when we need them, here's a case where we measure the pressure, and pressure is constant for 100 milliseconds. I'm pretty sure that's a world record. So you have to use a couple of tricks to do this. And so when would you do this? Well, when you need that much time, it's possible. Okay, that's kind of a quick introduction to shock tubes that shows you that it's pretty easy to generate a wide range of temperatures and pressures. We're back to my harmonic oscillator. So I want to introduce vibrational relaxation. We talked about vibrational energy and spectra. So the way we think about vibrational relaxation is that vibrational energy is given 1/2 kx squared. So it's basically the energy in this potential well. Harmonic oscillator gives you a parabola. In reality, it's not a parabola, but it's close. So this massless spring thing I introduced earlier leads to energy levels of quantum mechanics. These are harmonic oscillators that are equally spaced. Looks like in this case I labeled the energy levels I equals 0, 1, 2, 3, 4, rather than V. It's usually V. Energy levels are quantized. And we use Boltzmann statistics to calculate the fraction of population in each of those levels. This is what the distribution would look like if we plot it on a semi-log plot versus vibrational energy level for some molecule at room temperature. So at room temperature, essentially all the molecules are at level 0. If you go to high temperatures, the distribution looks like this. The question is, how does the gas move from one condition to the other? The shock wave excites changes the temperature. And we usually assume that the translational and rotational temperatures are instantly changed. But the vibrational temperature takes time because you have to have highly energetic collisions to populate these excited states. So it takes time. So there's more molecules in the lower levels than in high, but when you heat the temperature, it has to adjust. Boltzmann tells us that if we know the temperature, that's the distribution. So the question is, how do you populate levels 2, 3, 4, 5? Well, if we assume that there is a vibrational temperature, then there is a temperature that characterizes the instantaneous distribution. And what will happen is that T vibe will evolve between T translational up to the final value. And that's called vibrational relaxation. And it's important because it takes enough time that it appears in some supersonic, hypersonic flow problems. So the physicist Hans Bethe and Edward Teller. I think they might have been at Cornell University at the time, probably along about 1950, somewhere there, derived this equation, so for vibration relaxation. And it says that the rate of change of the vibrational energy, that's the vibrational energy per mole or per mass, the rate of change of vibrational energy is proportional to the difference between its value and the equilibrium value. So when you see that linear equation like that, it's often called a relaxation equation. So it says that the rate of change of EV is proportional to the difference between its current value and its ultimate value, divided by characteristic time tau. So that's the relaxation equation. How did they derive that? They derived it assuming a harmonic oscillator, which because harmonic oscillator simplifies the problem immensely. And you can actually go to what's called semi-classical theory, and you can relate the probabilities in the collision of going from 0 to 1 or 1 to 2, depending upon the temperature and the properties of the molecules. So the question is, if that's the equation, and tau is the number we need to know, which is going to depend upon temperature, because everything's going to happen faster at high temperatures, because the collision energies are higher. How do you get tau? How do you measure it? Because it can't be calculated. Well, people try to calculate it, but it's usually better measured. So this time tau here is derived by some other people using what's called semi-classical theory. And so the time, okay, Z is a collision frequency. I introduced the collision frequency. It's the collision frequency of an individual molecule as it moves through a cloud of other molecules with a number density m. So this is really collision frequency together. That's the collision frequency of the single V moving through A. And P10 is the one fundamental parameter. It's the probability that a molecule at level 1 will go to 0 in a collision. It obviously must depend upon temperature. So it's the harmonic oscillator allows these physicists to derive an equation for relaxation time. It depends on only one number. So that's the thing of beauty, the harmonic oscillator. So now the question is, how do you do this? And so the semi-classical theory, if I go from here, so M is the number density. So I'm going to use P equals NKT and rewrite this in terms of pressure and temperature, and I'm going to move the pressure over here. So it's convention to plot this not as tau, but to plot it as P tau. And if you do this, then P tau is now a function only of temperature. So the real question is, how does this depend on temperature? Theory says that it should be proportional to T to the minus 1/3. I won't tell you why, but that's the way it is. So the question is, how do we measure tau? So you can measure it. So people did this by looking in a static cell and fluctuating pressure and looking. They would suddenly heat the cell, and they would use a pressure gauge. So the sensor was a pressure gauge. But the way we do it is with shock waves. I didn't say that right. People used acoustic theory to relate the speed of propagation of waves and pressure to get at this term. But we use shock waves, and so the process is you heat the gas, and here comes the shock wave, and we think of as discontinuity. The temperature jumps up to T5, translational temperature, and it relaxes while the vibrational temperature comes up. There's conservation of energy here. So if you shift energy from the translational energy, rotational mode to vibration, temperature goes down. So we could see it here, and most people studied it this way years ago. They would watch the decay of the translational temperature to infer the rate of change of the vibrational energy, which gave them tau. Or you can go behind the reflected shock wave and watch it again. The bottom line is that the key is to accept. You have to accept this. The phenomena of vibrational relaxation is that there's always a vibrational temperature. If you put energy into vibration of a molecule, it zooms to Boltzmann distribution. If you accept that, there's always a vibrational temperature. So we're going to try to measure the vibrational temperature. Okay. And of course, when you go higher temperature, it's faster. All right. This is how it was done back around 1960. That was actually around maybe just before 60. Lasers weren't invented until 1960. So nobody was studying this problem with the lasers until 1970 or so. And the people who got a lot of credit for this were Millikan and White, who worked for General Electric Research Center. And they measured and plotted the results on this. This is called a Landau-Teller diagram. There's Teller again. Landau is a Russian physicist. And he's one of the ones who gets credit for showing that p tau should scale with t to the minus 1/3. It's not intuitively obvious. That's the simple model gives this. And so Millikan and White did their experiments, and they plotted data for, say, pure oxygen. The data is pretty scattered. Nitrogen and air, pure nitrogen. So it obviously depends upon the gas mixture. So the data are pretty scattered, but the correlation built by Millikan and White was, they did best fit to all the data. But how did they do the experiment? So this is 1964, looks like. So who knows what this is? Tell me what it is.
So you have a set of mirrors that
Okay, it's an interferometer. So in those days, the optical techniques that were common were shadowgraph, Schlieren, and interferometry. So this was some sort of what's called a Mach-Zehnder interferometry. So light beams are combined in a way that, and then recombined in a way that, and then recorded on film. And so you can the vertical distance here, these are fringes that appear due to the interaction of these two beams. And the motion of these, what do I call them? Fringes, is proportional to density change, because the wavelength depends upon the index of refraction. So there's something called the Glasser-Dale constant. So anyway, the shift that occurs in this pattern, vertical shift, with distance. So this is distance behind the wave. As you travel behind the wave farther and farther, there's a shift in the frequency, and they measure it in fringes. So it's like this one here, this fringe shifts by one fringe. And that is a density change or index of refraction change. And so the rate at which so they have basically measured d rho dx. Actually, it's the index of refraction versus that. And so in the limit that rho changes exponentially like a temperature does, they just determine tau. That's how it was done in those days, Millikan and White. Very famous paper. And they, to this day, we still use the Millikan and White correlation for how vibrational relaxation times depend on temperature and mixture. And they would do experiments in air and nitrogen and all different gases. Well, that's how it's done. So what's the modern way? The modern way that we're pushing at Stanford is to measure quantum state resolved populations. So we're going to measure, say molecular oxygen, we're going to measure the time history of the number density in V double prime of 4, which is initially 0. So we're going to watch the Boltzmann distribution form by probing different quantum states. And of course, if there's the Boltzmann temperature, you actually only have to measure one of these. But we've never had quantum state resolved distributions in shockwaves. And so we can use this to test these theories and to measure tau. So we've been working on this the last few years. So oxygen is important. Well, so this is all motivated by the chemistry of high temperature air. So if you have a hypersonic vehicle or entry body moving at high velocity through the atmosphere, there'll be shock wave in front, and the evolution of the air through that shock wave and the test is to the temperature changes, the vibrational temperature changes, and chemical reactions take place. So that's the practical problem that we're interested in. And so we're going to do this by studying diluted mixtures of oxygen and argon. And we're going to probe, so now we're getting into the lasers. This is not quite the state of the art. This is close to, this is, we're at the state of the art, but this is, we're past where this view graph was. So we have a laser here. Let's see if I get this right. Okay. So we have lasers. These are UV lasers. This is called a mirror laser. It probes. We can set it to probe d double prime of 4, 5, or 6 transitions. The green laser here is set probes only d double prime. So we have lasers that probe different vibrational levels. These are continuous wave monochromatic lasers set to the center of some line and passing through the shock tube 5 millimeters from the end wall. So we're going to measure absorption and we're going to watch the evolution. So of course we have to have cross sections or absorption coefficients to do this. And somebody was asking about the beam. So sometimes we'll pass them through different paths in this experiment. Blue goes this way and the green one goes this way. So you send in a light and let's say it's SI0, fill the shock tube. There would be some pre-shock attenuation, but only if those levels are populated, which they're not. So we get I0, shock tube comes along, and we begin to form molecules in those excited states. We apply Beer's law because it's monochromatic. In this case, we're using cross-sections, so we're interested in measuring the time evolution of the number density in V double prime. We have to know the cross-section, which depends upon temperature. So we do that in some early experiments. So we have to do that. We have to do the spectroscopy. Once we know the cross-sections, we can do the kinetics experiments. And this is what we get. This would have been, nobody's ever done this before. This would be a time evolution of the population of V double prime of 4 and 5 in microseconds. What was the temperature? 5,300 degrees Kelvin, half an atmosphere, 2%. So buried in here would be, this is the temperature high enough that first the population has to go up and then it has to go down. Why does it have to go down? O2 is dissociated. So this is, it's called the coupled vibration dissociation problem. So I'm only going to have time to show you one. So this early slope is the vibration relaxation time. And so 4 goes up a little faster than 5. If we take the proportion of 4 and 5, we get the vibrational temperature, which changes with time. So we confirmed that the vibrational distribution is Boltzmann in these levels, and we measured the evolution of the T sub 5. But we're also interested in the chemistry, so we look at this entire profile. This is that same case, and I plotted it now as, well, the students plotted it versus temperature. So that would be, the red would be the vibrational temperature. The dotted line is the translational temperature. And now you ask, well, why doesn't this one go to this one? That's because while it's dissociating, the molecules dissociate, take away vibrational energy. So there's a continuing disconnect, mismatch between, and that turns out to be the way we get at some fundamental parameters in chemical kinetics. It's called the coupled vibration dissociation problem. So what I'm showing you is that you can get high quality signal noise ratio for using UV lasers. Now we're back to electronic transitions. Everything's a lot more complicated, but look what we can do. Measure populations of oxygen. And we've done this up to 14,000 Kelvin. And then we can put these points on a Lambda-Teller plot. So this is probably a year and a half of work right here. Jesse Stryker is the student came from Michigan. So what did he do? He measured the tau that corresponds to oxygen and argon. The tau that corresponds to oxygen, because when you change the collision partner, you change the efficiency of transferring energy in a collision. So you have to have a high-speed collision that has enough energy, but it still depends upon the properties of the collider. So there's different answers, O2, 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 N2, okay. Now there's another effect. It's called VV transfer. So let's say we have O2 and we have N2, and we shock heat them. They each have their own vibrational temperatures, but they're actually not equal because one relaxes faster than the other. So the one that goes first has more energy and it transfers vibration. So if you have a collision between a nitrogen in some quantum number and an oxygen in another quantum number, it's easy for them to transfer vibrational energy. It's different than transferring the translational energy. So that's a very important process called VP. So you change the experiment to get at these parameters, but the modelers of these flow fields who are doing high temperature reacting air, they want to know all these parameters. They need to know all of these taus that take place. And it turns out that when we compare with the work from 1963 by Millikan and White at a low temperature, I didn't plot it here, there's general agreement. But what happened to the T to the minus 1/3? In fact, if the data now start bending up, that's not in the model. So this is a revelation that the theory breaks down at high temperatures. That simple semi-classical theory that led to T to the minus 1/3, done by Landau probably, breaks down. So to this day, people modeling re-entry problems will still use the Millikan-White correlation. So this is showing that it's wrong. It doesn't mean it's always important in every problem, it's just, but that part of the model is definitely wrong. It's the first time. I know there's some Russian scientists tried to do this with lamps, not lasers, but lamps. And they got up to, they showed some similar trends, but much higher scatter. We got up to 14,000 degrees. So the main thing is that the biggest problem is that the Millikan-White model breaks down at high temperatures. Okay, that's it, I'm going to go time. We can also study ignition in shock tubes, ignition delay. There's people here interested in ignition delay. Typically, you would shock heat some mixture like this is hydrogen and oxygen, 1100 Kelvin, 3 atmospheres. Shock heat it, and you see when we're measuring the conditions near the end wall. At the sidewall, but near the end, see the pressure jumps up. Now it jumps to region 5. That's the static count, and then it goes bang. So the gas sits there and cooks, and then it ignites. And so you can look at the pressure signature as one way to measure ignition delay, and that's a common way. That's a common way. It's a simple way. Other ways include measuring the emission of excited state, OH, and usually get about the same answer. That's common. So that's how you would measure ignition delay times as functions of temperature and pressure. Now you might ask, well, how does the ignition delay time change with hydrocarbon species? So this was a plot, I think, from maybe 10 years ago. We looked at normal alkanes. So this is a butane, basically butane, pentane, hexane. So basically the molecules are getting bigger. Molecules are getting bigger. And what do we find? And this is now ignition delay. Now, when you have chemical problems, it's very common to plot the logarithm of a time or rate constant versus 1/T, because the simplest theory, called the Arrhenius theory, says that those rate constants should be aligned on a plot like this. That's an approximation. What do you see? You see as the molecules get bigger, the times get shorter. So the bigger molecules, which have more CH bonds, more places to be attacked by radicals, ignite faster. But some people would say, well, they're all about the same. So it took high-quality experiments to reveal the fact that no, they're all of these alkanes, that means a saturated hydrocarbon, they don't ignite at the same rate. Now that only went down to about 1250. If you go lower, there's something called the NTC region that some of you probably know about. So the ignition delay time has this funny character that it turns over and actually can even go decline before it goes up again. Why does it do that? Well, that's because as you go from high temperatures to middle temperatures to low temperatures, the dominant chemical reactions change. There's changes in the most critical reactions. So you have a mechanism, 100, 500 reactions, but the ones that are important change when you go from high temperatures to. So when you're up here, high temperatures, these are so-called, these are radical reactions, H plus something, dominated by radicals. Now this is different. This is in the region where we'll call peroxides come into play. So the nice thing about the shock tube is we can hit all of these conditions. But there is a problem. Some of the interesting things occur at longer times than we could easily generate. So we have to fight that problem. So we want longer test times. Now our competition would be people who have rapid compression machines. Rapid compression machine is, has its advantages and disadvantages. It compresses the gas with a piston, but it doesn't do it instantaneously. It takes time to compress the gas at high pressures. And then they tend to be smaller devices, and then they watch it for 100 or 200 milliseconds, during which time heat transfer takes place with the valves. So it's not an isothermal reactor. I'm kind of a non-RCM person. It's not an isothermal reactor, it's not instantaneous, but it has the virtue of getting to long times. And shock tubes generally didn't go to long times, but so we've tried to fix that problem. And there's one of the fixes is right here. So what do? Here's a plot of the test time capability of a shock tube, of a standard shock tube, unmodified shock tube, versus temperatures. Basically, get up to 2, 3, 4 milliseconds of test time. Here's the ignition delay time of endodecane. Here's the NTC region. So if you wanted to study at temperatures like this, we can't reach it. We don't have enough test time. That's the RCM, approximately. Right? They can reach these lower temperatures than we can. So we've got to fix that problem. So we modify the shock tube in a certain way. And the main idea is that you make the driver longer. So the ultimate limit for the test time has to do with when the expansion wave goes down into the driver to the end and comes back and goes down the tube, and you're done. You got to make that happen later. So we've got a couple of ways we do that, but this is the simplest way. So now we can overlap with RCMs, and what happens when you go to compare your data? Inevitably, they don't agree exactly, because there's imperfections in every experiment. So we have to work out that problem, but for the most part, we can access now essentially any temperature we want. Now, there's another problem. So how many people know about the dP/dt problem? One person. Okay, so in an ideal world, the conditions behind the reflected shock wave would be adiabatic, and the pressure and temperature would stay constant. Temperature might change due to the chemical reaction, but the pressure would stay constant. But in reality, pressure typically goes up. And for the longest time, until maybe 10 or 15 years ago, people just ignored this problem and said, well, it's too small a problem to worry about. So they would calculate the ignition delay based upon the initial pressure, and they model it. They try to compare the model with the measurement. So here's the measured time right here, ignition delay. But it bothered me that the models didn't work well in a regime like this, 1,000 degrees. And I finally decided, maybe some other people might have thought about this, but we introduced the terminology dP/dt, that if the pressure is changing, that means the temperature is changing. And if you assume isentropic, you can show that delta T over T is gamma minus 1 over gamma delta P over P. So in other words, if this changes 10%, pressure, temperature changed 4%. But the temperature sensitivity of ignition delay is so high that 1% in temperature changes the ignition delay by, say, 15%. You can't tolerate a 3 or 4% temperature change and expect to get anything meaningful. You have to account for it. So we have to fix that problem. You have to put it in your model. So one way you deal with this problem is you start measuring dP/dt and you report it. And then you model the chemical reactions, including that effect. That's okay. Better yet is to fix it. This is, I think, due to the fact that the instant shock wave is attenuating due to sidewall boundary layers, and that's causing this problem. But whatever the cause, it's there. It varies between conditions, it varies between facilities. No two laboratories get the same number. And I think it's the reason why ignition delay times measured in several different laboratories never really agreed well in this temperature regime. If the times are short, it's not a problem, but these long times. So anyway, I had a student and we got interested in this idea. He came up with this idea of a driver insert. So inside this driver, we put like a bullet. And the location of the bullet, the shape of the bullet determine when the waves that are reflected from, if the expansion wave goes back in, when it hits the surface, it sends the wave this way. And comes back. If you arrange for them to arrive at the right time, you can compensate. So the blue is what we did with our driver insert. So you make the pressure constant. And what happens to the ignition delay time when you make the pressure constant? You get a different answer. So when we did that, here's the ignition delay time that a group in, I think it was Ireland, got when they had a small diameter shock tube with a large dPdt. This is propane. Here's, at high temperatures, things are pretty good. Now, when you get up here, if you do it without the insert, you get this. If you do it with the insert, you get that. And it starts agreeing with the kinetic modeling. So the kinetic modelers were assuming something different than was in the shock tube. And people just didn't pay enough attention to that for a while. And so people would say, well, the kinetic model's wrong. No, your shock tube is wrong. A famous professor, I won't tell you his name, was an RCM advocate, and I was presenting some results. And before I decided to get into it, he said, shock tubes are garbage. That's what he told me. I took that personally. So we fixed this problem. And so I think now the literature, the community understands this problem now. You cannot neglect dPdt. You should report dPdt and accommodate it in your modeling or fix it. And when you fix it, then you get agreement with the models. And so that's a thing I'm happy about. So now that just means that if you do an experiment and you have dPdt of 0, when you report the number, it can be modeled. And the model they usually assume adiabatic, probably okay. They usually assume constant volume. But it's not a constant volume problem. The shock wave is moving away. One part of that region is not solid. It's a good approximation, but it's not exactly right. So that's another issue we have to worry about. I call it the problem. Most people assume constant volume or constant pressure. But reflective shock tubes are not exactly constant volume or constant pressure. The times are short enough you can usually neglect heat transfer. Here's a heptane ignition. So that's what we see if we do heptane. So what do you see? There's the measured sidewall pressure. Clearly not a constant pressure problem. It's constant pressure up to the time of ignition, but it's not constant pressure through ignition. So if you want to model the chemical reactions continuously, you're done. Once you get to the ignition, it's over. Constant pressure model is obviously not right. Well, what about the constant? So if you do a constant volume simulation, that's not right either. The blue. So the reality, which is the red, is somewhere in between. It's not exactly constant volume, it's not exactly constant pressure. Now, it may, given a given mixture, may come close to one of these limits. So it's not like you can never use constant volume. It's just you have to be very careful about this and the implications of the assumptions. So the modelers, they'll usually say we model constant volume. Well, they have to justify it. They should justify it. Or the experimentalists will do it and they'll say we assume constant volume. And it may be okay, but I think people should be more careful. So I came up with something called the constrained reaction volume idea. So I tried to imagine how could you make it constant volume, and then I realized, well, why don't I try to make it constant pressure? So when you do a reflective shock experiment with an exothermic mixture, highly exothermic, all the energy release is right here. So all the test mixture is compressed, and as the shock wave goes back, all the gas between the shock wave and the end wall burns, gives off energy, changes the pressure and the temperature. What if you limit the gas to just this down here? Don't fill the whole chamber with reactive gas, just put it down near the end. Now, when the shock wave does its job, it leaves behind only a small region releasing energy. And you hope, well, with the hope, it works, you hope that the pressure will relieve itself axially, and you get close to constant pressure. That's the hope. And that would eliminate, okay, there's two reasons. One, you make the problem constant pressure, which is, you have to model it. You have to model this problem, so you have to model it by, say, taking constant pressure. Also, it's known to the shock tube community. How many people here do shock tube experiments? Just one. Two. So it's known that there's something called remote ignition. So in this low temperature regime, it will ignite over here somewhere. Because as the shock wave goes back, it's producing actually higher temperatures. So it burns faster than the gas near the wall, even though that gas was heated first. So there's a problem, and we can avoid that problem by saying there's no reactive gas out there. So here we go. Here's the conventional shock tube experiment. Large pressure changes. So the thing is, how do you model, if you want to model all the way through the combustion process, not just when does it ignite, how do you do it with that crazy pressure signal? I don't think people just didn't do it. But now, if you use this new method, constrained reaction volume method, the pressure is nearly constant. It's igniting here. I can see it with emission. I don't see it in pressure. Energy release was confined to that little area. So I really like this idea. I think it's important. Okay, so that allows us to study the chemistry. We model the chemistry all the way through the reaction, all the way to the products, which we want to do because ignition at late time is just one number. That's not a good way to measure chemical kinetics. You want to measure reaction-specific things, so you need more information. Okay, here's a new idea. We haven't yet published this. Could we use a shock wave to reform natural gas? You could heat methane to 3,000 Kelvin. What does it want to be? You do a equilibrium calculation for methane. Take methane, CH4, put it to 2,000 degrees Kelvin and 10 atmospheres. What do you think you get? All the hydrogen goes to H2. Carbon, if you wait long enough, is going to go to solid carbon. So there's no oxygen. It wants to be hydrogen. But you have to, it's very temperature sensitive. So you want, this is an idea. We don't even have money for this yet. The idea is that and the idea is, what if you had a device that replicated the shock tube on a natural gas pipeline? Take the gas pressure out of the pipeline, put it through your shock device, and out comes hydrogen, some amount of hydrogen. No CO2, there's no water. You do have to somehow make it work. You have to have some power to run your compressor or something. That's the idea. I think it's an idea. It's not been demonstrated. I think I could use it for other things. Anyway, we're studying it in the laboratory, even though I don't have any money for it. Here's a simulation of what we get if we did this at 70% methane and argon, 3 atmospheres as a function of temperature, and a 10 millisecond test time. So it looks like if you get up to 2,000 degrees, it's 75% yield, which would be phenomenal. And we've taken some quick samples of the particles, the carbon that we're getting. because I'm curious whether we could actually produce desirable carbon. Okay, so I've added some stuff to these lectures. We just started this project, so I'm not sure that I should be giving away all my good ideas, but that's a good idea. And here's another one. It's a little older, it's about 5 or 6 years old. Most people measure flame speed in an atmospheric burner or in a constrained, in a constant volume chamber. Fill the chamber, let it set, ignite it at the middle, watch the flame. You can't ever do that at high temperatures because while you're waiting for it to settle at 800 degrees Kelvin, it ignites on you. So how can you measure the flame speed, which occurs in an engine? The flame is propagating at high temperatures. So how can you do this? And so it occurred to me once about 6 or 7 years ago maybe. Why don't we do it in the shock tube? So we do this now, and it's getting better and better. So we fill the shock tube with combustible gas, use a laser to ignite at a point, monitor the growth of the flame with a high-speed camera. There's some variations on this theme. And then we use chemiluminescent imaging. That would be OH star or CH star. And we do flaring also. Let's see, I wonder if I can make this go here. So that's what we would see partway through. Let's see if I can get this right here. Well, my movie's not playing, I don't know why. Well, it's supposed to be a movie that just shows that starts from a spark and grows. If I do this. No, okay. So we've done this in a variety of fuels. And this is what we get. Okay, what you're after is called the laminar flame speed. It's the speed at which a laminar flame would move if it has no stretch. So you have to watch this spherical thing grow. You have to fit it to, you get the speed in the burned gases, and then you have to transform that to the unburned gases, and you have to remove the effect of stretch. So there's some steps involved to go from the experiment to this, and then you measure it versus T, and then you begin to compare it with different mechanisms. And the fact is, there's never been a flame experiment above about 800 degrees Kelvin before. So we're working on this now as we speak. And the hope is that if we get to high enough temperatures, we can reveal the deficiencies in the kinetic models. Because in an engine, it occurs at high temperatures. Okay, so we're playing with this now. How do we do the best job of fitting this? And Swift, that's the name of my student who just graduated. He wants to call this the Swift method. He uses sidewall imaging flame technique. I think we're up to about 1,200 degrees Kelvin. Okay. Okay, that's it for the second lecture. Questions?
For the constrained reaction though,
Okay.
how are you keeping the reactive mixture to a small region? Do you have a second
Okay,
diagram in
good,
there?
good. There's two ways. So we spent 2 years doing it with a valve. So it's a sliding valve. I was feeling so good about this that we had invented this idea. And then I ran into an Indian colleague at a meeting. It turns out somebody else had done something similar for different reasons. I think it was in Wales. They'd used a ball valve about a meter away because they were experiencing detonation waves in their shock tube experiments, and they wanted to do. So anyway, this makes a lot of sense. So we did it with a sliding valve. You have to design it and build it. And then we think, well, that's nice. We just fill it up, open the valve. But I didn't think ahead. We now have an acoustic mismatch between these two gases. And so we got into some problems. We get some little wave reflexes. So you actually, in addition to this valve, you have to pay a little attention to matching the acoustic impedance across these things. And the valve, that works fine. It's about 30 centimeters. Okay, so if you start with a gas that's, say, 30 centimeters. What's rho 5 over rho 1? That's the amount it's compressed. So if you take a sample this much, it ends up. So we want it to be small. Yeah, it works. But it turns out there's some other little problems. You know, it's not, we don't always use, there's another method I'm not going to talk about. There's another method that gets the same effect, but it's a little simpler. Any other questions? Look like, yeah.
In the vibrational relaxation type, is there a prep for delta J that you want to target, or any delta J would be fine?
Let's see, I'm not sure I got it. You have to pick a J.
Yeah, so is there like delta J of
Oh,
one?
delta, okay, vibration relaxation.
For those measurements?
Yeah. Well, in the measurement, you see, the measurement would just pick a particular transition. It's electronic transition. It's not a just rotational. It goes from one electronic state to another. Oxygen has something called the vacuum ultraviolet. So if the wavelength is less than around 200 nanometers, it doesn't go through. Okay, so we're out at around 225, but it starts to absorb strongly at high temperatures. So we only can do high temperatures. It's electronic transition. So what I can't tell you right off the, I don't know what the delta V is, which I know from the Frank-Condon factor. We calculate the spectrum, and then we pick the strong place. I just don't remember what the delta V and the delta J is. There was another question, yeah.
So for driver insert, how does it work? Because the expansion waves would have lesser distance.
So when the expansion wave goes back, it sees a little blockage. It's kind of like it's reached its end and it comes back now. It's like in the regular full shock tube, expansion wave goes back, comes back as another wave. Right. So you're starting some of that early. It's kind of like a series of end walls. If there's no insert, the wave goes all the way back and then comes out down. But if you start to block it a little bit, it's sending out signals that correspond to the end of that left running wave. We have to design the shape and the location. Yeah.
And for another question for including the reactive gases so that they stay just near the end wall.
Yeah.
What are the techniques that you're using? Like, are you doing stage filling, and what are the challenges there?
So that's the name of the alternate process. I think that's what you mean, right? What did you say that again?
Right, you call it stage filling, right? You fill the reactive gases first and then.
Yeah, we do that. That's a simpler way. It's not as good, but it's a simpler way. You have to measure you always have to measure what you have to know if it's working. Any other questions?
So like this shock wave reforming process that you are using in your lab. So are you going to produce any kind of aviation fuels like through that particular?
No. It's just, there's a lot of interest right now in how do you reform natural gas? There's steam reforming, and then there's green methods, you want to use solar energy. There's a lot of competition right now on how to do this. But a lot of them use catalysts. So I want to get away from the catalyst.
So it's the same concept we use, like the implantation of the solar cells over the cap, over the vehicles, and then we drive the vehicles through the solar energy storage and then the aviation fuels. So like this kind of features can be used for production of the more aviation fuels for a cleaner storage and like cleaner.
Yeah, that sounds good. Yes.
Do you expect a lot of influence of recombination reactions in your reforming methane to hydrogen?
Well, you basically think of it as you heat it and you're moving, always move towards, chemical reactions always move towards equilibrium. At equilibrium, forward and reverse are balanced. So you're moving to a final new state in which reactions are going both ways. But the equilibrium solution, as you go up in temperature, you just get more and more conversion to the hydrogen. So the key is, see, the people who are doing this with catalysts do this at like 1,000 K. But the catalyst problems with, so you can make it happen at lower temperatures with a catalyst, but the catalyst lifetime is a problem. So there's competition right now for how to do this. But to do it better than steam reforming. Steam reforming still produces CO2. And it also has the economics. Steam reforming produces CO2, but it's cheap. So you have to produce the hydrogen in a competitive way. But I like this model of the natural gas pipeline. It's already at high pressure. And we use that pressure to produce shock waves. That's my idea, really.
It's like dissociation and recombination happening.
I think it's driven by the dissociation. Yes.
It's talking about exhaust emissions, since you are using high pressure air as the driver.
Mm-hmm.
Are you anticipating any sort of emissions in this interface between the air and the fuel, especially for the ammonia case?
I'm not sure I understand the question. Is there,
The air in the driver, right, for
Yeah.
the high pressure. So are you anticipating any kind of combustion in this interface?
yeah, you can. So that's a problem sometimes. So, for example, people who do hydrogen-driven, if you go to, hydrogen is the ultimate driver gas because it has a high speed of sound and low molecular weight. So people who use hydrogen to drive strong shock waves in air encounter this problem. It burns at the interface if the hydrogen is hot. So, it's a problem. You solve it usually with a buffer of some kind. But, yeah.
Can you talk a bit about tailoring, how you achieve that? Tailoring, you said.
Oh, tailoring. Tailoring. So people discovered tailoring. It wasn't me. I think they discovered it in Germany, maybe around I'm not sure. There was a famous guy named Abe Hirschberg at Cornell who I think gets credit for it mostly. But basically, you match this acoustic impedance, and so you have to pick the composition of the driver. It's usually helium and nitrogen. So you start blending in nitrogen. So what you have to match is at the interface between 2 and 3. The 2 is the, no, I didn't say that right, interface between, you have to match the acoustic impedance as the reflected shock goes into the contact surface. What is it, rho A? So you adjust, so for a given temperature, you have to adjust the acoustic impedance of the driver gas so that rho A matches. So that means you blend in nitrogen for the most part. Almost always it's a mixture of 10, 20, 30, 40% nitrogen. You know when you get it because the pressure, by the way, it's not an interface, it's a zone. We analyze it like an interface, but in fact it's a zone. So you can never really get rid of it. It's always a little bit rough there. But we can deal with that. Any other questions? We kind of ran over in time. I've got one more lecture to go. I guess we better take a short break and then. So, much of the research in my shock tube laboratory is focused on chemical kinetics, but we also have work on spectroscopy and diagnostics development. But I'm going to talk here today, this hour, mostly about kinetics. So we'll review quickly the absorption theory, and then we'll talk about capabilities. Okay, there are 3 types of kinetics that we talk about. Foundational rates, so we'll measure the rate of an elemental reaction. Once that's done, if it's done well, it's like a thermodynamic property. You no longer change it. It's done. It's not a variable anymore. But a lot of combustion problems have involved many reactions, and they're modeled with large mechanisms. Some chemical kineticists who their career is about building large mechanisms. And there may be thousands of reactions in their mechanism. Each one has to have its rate coefficients and thermodynamic properties. Now when you go and you're doing a combustion experiment with flame speed or ignition delay and you calculate it, it depends on so many things. How do you ever get an accurate mechanism validated? So that's a problem. We try and we work on this problem. And we're always looking to measure new species. That's always going on. All right. So you're now very comfortable with Beer's law. We usually have to assume properties are uniform along the line of sight. Small molecules, we have to know the line strength, the line shape factor, and the length in order to infer the species partial pressure. So we need to have a quantitative database for S and Phi, or we have to measure it ourselves. So using this evolving technology, since I've been doing this starting around 1973 or so, we probably learned how to measure about 30 species. So there's always a question of, well, what wavelength should you use? What transition should you use? What laser should you use? But gradually over time, we've learned how to measure a lot of different species. And for the first several years, we used fixed wavelength lasers. So I built an electric discharge carbon monoxide laser that could be discretely tuned to 5 or 10 wavelengths. And we could use only the fixed wavelength, which meant we had to calculate line strengths and line shape factors in order to get to K. But that would work. Eventually, finally, around 1980, we got tunable lasers, so tunable UV lasers. So this is one of my students using one of the very first spectrophysics 380 ring dye lasers. So this is a CW laser, frequency doubled, monochromatic, which was a huge advance. Nowadays, we use Ti-sapphire lasers. So Ti-sapphire is a tunable crystal laser. So no more dye laser. So generally, these species are most sensitively detected in the ultraviolet, and the UV lasers are just expensive and difficult, but they're essential to what we do. Okay, this is our very latest laser. It's the Ti-sapphire laser from a company called M Squared. So that thing that's sitting on the table there is probably $300,000 or so. So the good news is it's wavelength tunable, and it's monochromatic, and they're fantastic. But they're not portable diode lasers. So why do we do this? Well, we look at the sensitivity. So this is the chart that shows what levels of species can we measure at 1 atmosphere and 50 centimeter shock tube with megahertz or time resolution. So these curves show you that we've identified transitions that allows us to detect tens to 100 ppm of species using laser absorption. But if you look at the reactive radicals, like CO, OH, CH, now we can measure sub-ppm. So the beauty of laser absorption is that it can be very sensitive in measuring the species that we need to do chemistry. And they're very quantitative. So how accurate is this? Well, it depends upon how accurately we know S and Phi. We know length always well, so it's just S and Phi. So we calibrate or we measure those things ourselves so that we can do accurate. A target for us typically is, can we measure things to better than 5%? We hope to measure things better than 5%. Sometimes we can get to a few percent. That's kind of, so it's not perfect goals. So we have, I'm going to show you 3 types of kinetics now. Foundation field kinetics, methyl ester kinetics, and then something about our method called Hi-Chem. Let's see. Up here I've got a few different shock tubes. This is the one that I showed you earlier today. That's the, call it the kinetic shock tube. That was a imaging shock tube. That's a high pressure shock tube. And this one is the shock tube. I've had this shock tube since 1972. So it's a really good shock tube. Came from NASA Ames. All right, so The gold standard for chemical kinetics is to measure the rate coefficient itself. So if you are modeling the combustion of hydrogen and oxygen and maybe a few hydrocarbons, these would be very important reactions. These would be the reactions that show up in sensitivity analysis when you do a kinetic simulation of some combustion problem. So I'm going to show you what we've done to determine those rate coefficients of those two particular reactions. So how do we measure an individual reaction? It's like a two-step process. You do computer simulations. Your goal is to use the computer to plan the experiment. Use sensitivity analysis to isolate. You're looking to find a reactive mixture which will react in a way that your measurement is sensitive to only one rate coefficient. Then you do the experiment. And here's an example. So the kinetics modelers will know this is regarded as the most important chemical reaction in combustion. This is the one that shows up in almost every sensitivity analysis. Therefore, you'd like to know it really well. And so it's been a target for years, for decades. And so we've done this. I had a student who did it in 1990. I've had 3 students do 3 different methods. The competition before we did it was a method called atomic resonance absorption spectroscopy. So you can use a resonance lamp, not a laser, a resonance lamp. But any lamp is never as steady as a laser. So that was the method that produced the best rate coefficient data before we used lasers. We get the same answer, but we get much more precision than was possible before. Well, this was a clever one. This was, I never expected this. We're going to study the reaction H plus O2, and so you have to pick the mixture. Well, the interesting thing, so you pick the mixture with 0.9% hydrogen, 0.1% oxygen, so 9 times as much hydrogen as oxygen. But sensitivity analysis revealed the way to do this. The surprise was, what was he measuring? Usually, if you do a chemical reaction, you're going to measure one or two of these species. So here's the problem. You'd like to study H plus O2. You can't buy H. You can buy oxygen, but you can't buy H. So you'd like to put them together at time 0 and watch what happens. Well, the trouble is you can't buy H. So you have to play tricks. How do you make this reaction the dominant one when you can't buy H atoms? Well, there are 2 tricks. You can say, well, I'll study the reaction in the reverse direction. Yeah, but I can't buy OH or O either. So it's hard to do these reactions with radicals. But this student was clever. He ran his computer simulations so long he realized we should just measure water. Well, there's no water in that reaction. But his simulations, if we can believe them, said that water, H2O, the plot of H2O sensitivity versus time, that water was highly sensitive to that rate constant. So if you believe the simulations, that's a great experiment. And so he did it. This is Kai Hong. And so here's an experiment in which we measure the time, he measures the time evolution of water. So you shock heat this mixture of hydrogen and oxygen, and then you begin to form water. And if you do the simulation and you vary that rate coefficient by 30%, it's very different from what you measure. So it's like, this is looking very good, that we've stumbled on something. So his analysis considered, these were the 3 reactions that were most important. You might ask, well, what happened to, where do we get the atoms? You start with hydrogen and oxygen. So if you've had combustion courses, you probably have been exposed to this question. How do you model hydrogen and oxygen combustion? How do you get the ignition delay time? And the interesting thing is that it doesn't depend upon the initiation reaction. So somewhere, and you can model this in different ways, somehow hydrogen and oxygen molecules produce an H atom. And once you produce an H atom, it takes off. So it turns out, in most cases, it isn't the identity of that initiation reaction, Because hydrogen and oxygen don't actually react together to go to water. They dissociate one of the reactants. Okay, so all of this is to say this looks like a really good experiment and high quality signals. You can look and see that we form 2,000 ppm, which is exactly what we should form. We start with 0.1% of O2, so we should end up with 0.2% of H2O. So everything looks good. And so he plots it, and that was the green. That's the green. The green is he did this. Earlier, we did OH absorption up here, also in hydrogen-oxygen mixtures, and that looks pretty good. And then more recently, we did this a new way, OH laser absorption a new way. So the good news is all three of the students got the same answer within a few percent. So I'm feeling pretty good about that. That's the state of the art for that rate coefficient over that temperature range. So it proves that if you design your experiment well and you have good sensing diagnostics, you can make. We think the uncertainty, well, this is we say 5%, I don't know if it's 5%. It's probably 5% maybe at high temperatures. There's some uncertainty down here, low temperatures. So this is a reminder that people who do simulations, the computational people, we don't know these rate coefficients very well. 5% would be spectacular. We rarely know them that well. Okay, next example. There's another reaction that's pretty important. OH plus H2. So we find out it's important because when you model a problem, you do sensitivity analysis to see which reaction affects what. Large uncertainty. Turns out this one is important for flame speeds. So if you want to simulate flame speeds, you need to know this one. Okay, the best experiment is if you can bring reactions A and B together at time 0. So you'd like to do OH plus H2. Because then you don't have to worry about what else is happening. Well, it turns out that somebody found a way to produce OH really fast using something called T-butyl hydroperoxide, so some chemical. And if you heat this chemical to like this gas species to like 1200 degrees Kelvin, it's OH. So if you can accept that small issue, we call this a pseudo first order experiment because if you can produce OH and H2, and with no other reactions taking place, you can watch OH go away exponentially. And you've just determined the rate coefficient without having to do anything else. That's like the best experiment you can do. So we use T-butyl hydroperoxide, works over a limited temperature range of about 850 to 1350, pioneered by Bott and Cohn at Aerospace in Southern California, I believe. And this molecule looks like this. So when you heat it up with a shock wave, it kind of produces OH right here and the methyl. So you have to kind of convince yourself that the acetone and the methyl don't have an effect. But of course, you do the experiment and you vary things and you see if your model holds up. There's an experiment at 1,000 ppm of hydrogen, 26 ppm of TBHP. You see the rapid formation of the OH, boom, and it goes away. And it goes away, you can model it as if only one reaction is taking place. In reality, we always model it a little bit more sophisticated than that. But the point is, this is as close to the gold standard for reaction rate work as you can get. Students claim 3 to 5%. I'm a little skeptical. I don't think it's quite that good. But anyway, there's the results. A very low uncertainty. Now we say 17%. There's the existing data. So the black squares are our data. The other colors and symbols are other people. So what you see is that we get consistency with the center of gravity of these curves, but the precision, the precision of our work, the uncertainties are so much less than have been done by other people. All these other people used other methods. Usually atomic resonance absorption spectroscopy. So gradually over time, what happens is we're getting more and more accurate rate constants over time. Gradually, they get better and better and better. And once they're determined, they shouldn't be changed. When people vary rate coefficients and they try to fit data, this is dangerous. Because how do you know you're varying the right thing to get agreement? So people will say, we validated our mechanism using ignition delay. No, you can't validate it. There's too many parameters in that problem. And yet people continuously say, we validated our mechanism. You didn't validate the mechanism. You found that the mechanism recovered your answer if you made some adjustments. So the way to proceed has to be to measure these rate constants and nail them down. Here's another good experiment. This is an experiment on involving methyl esters. Let's see, I think I have pictures of these. Okay, so we set out to measure OH plus different methyl esters. There's just a sequence of methyl esters. I'll show them in a second. Formate, acetate, propanoate, butanoate. And we use the same OH trick to study OH plus. So my student, Amir Farouk, who's represented here by several people, he has continued to use this OH method, OH plus everything. Once you have this idea, you can really study a lot of different things. We've studied some. It started, so Bott and Cohen discovered it, but we were the first to use it really for laser experiments. Okay, so these are the species that come into play. So when you do pyrolysis, so pyrolysis, we're watching the breakdown of this molecule. When it breaks down, what are the things that can be present? Well, we anticipate those to be some residual methylformate, some ethanol, methanol, COCH4CH2. So we said, let's do an experiment where we measure everything and see if we get balance. So here's the structural pictures of these four molecules. And this is the final answer. Let's see. Hope I didn't take out a slide. So what did we find? We were able to plot these rate coefficients that you can begin to ask, how does the rate coefficient depend upon the structure? So that's what these are. Let's see. I'm going to skip ahead to see if okay, I changed the order of my slides, apologize. All right, so at this stage, we were looking at the relative values and could argue that as you, how does the rate constant change with the structure? So the rate coefficient is biggest for methylbutanoate. It's interestingly about the same for MA and F. These two are about the same. So the question is, where is the OH attacking this molecule? And how does that come into play? So anyway, I won't get into detail. So if you can do really good experiments, you can answer questions like that. How does the structure of the molecule relate to the rate constant? When we did this, there was kind of a big surprise. We got this rate coefficient here that we thought was good to 25%. The existing model at that time was off quite a bit. There was just no data. So the ability to calculate these rate coefficients sometimes is pretty bad. You know, you do an experiment, it helps the modelers help the experiment. You work together because we need the models to design the experiment, to do simulations. Okay, I had a good student and he wanted to see if he could do a complete oxygen balance on a problem. So we took this molecule and he measured the time histories of the main players. So we had, this is basically a multi-laser experiment. And he measured the decay of the methylformate. And he simultaneously measured the formation of CO and methyl. Each one of these you have to do the spectroscopy. What wavelength shall we use? What's the absorption code? You have to do all of that first. Once that's done, you use it. And we measured that there was low levels of formaldehyde, and we actually used, we measured methane and CO2, they were about the same. So interestingly enough, with time, what did we notice? The methanol and the CO grow together. Obviously, the products must be methanol and CO. And the formaldehyde comes slower and later. So the nice thing about this is if you add up the things we measured and count the oxygen content, we could account for 98%. So you're starting to feel good. We must have measured everything that's important because we found all the oxygen. So you're starting to feel good that the mechanism you have is correct. And the rate coefficients you inferred then from this are correct. That's like another good experiment. They're not always that good. You may have some questions, but sometimes they can be pretty good. So atom balance is a validation tool. Okay, I want to introduce Hi-Chem. I think I talked about it early on. So people were modeling hydrocarbon combustion for some fuel, for a real fuel, say jet fuel. How do you model the chemistry of jet fuel? It's a very complicated mixture of hydrocarbons. Maybe 100 species or more. How do you model something like that? So typically what people do is they will say, well, or maybe they do gasoline. Maybe I could represent gasoline by 3 surrogates. I might pick 3 hydrocarbons that behave kind of like gasoline. And I would pick them so that they would match certain properties. Maybe they would match the ignition delay time. So maybe I would find that if I blended 3 things together in certain proportions, they would match the ignition delay time. Then I'd look and I'd say, well, the trouble is it doesn't quite match the CH ratio. So the surrogate approach, which is the dominant approach, most people do it this way. You represent the real fuel with a surrogate. The virtue is, if you could represent gasoline with 3 or 4 things, then everybody could study it and they'd all be doing the same thing. So that's how science has progressed in modeling hydrocarbon combustion. In the theoretical chemical kineticists, they'd look at candidate reactions, they'd build libraries of 5,000 reactions and try to do their job of predicting those rate coefficients. And then you'd run that code. So now you would run that code with the surrogates. And then you might try to simplify it down. So that's how hydrocarbon combustion modeling has gone. And then, but there's not very much data. There might be ignition delay time, there might be flame speed. There's not a whole lot of, you don't have enough. So how do you ever know you've got the right mechanism? So that's a problem. So there's so many rate coefficients. So my colleague Hai Wang, Professor Hai Wang, saw some of our data and it gave him an idea. And it wasn't really a new idea, but we came on it and decided it was a good idea. The idea was that pyrolysis of molecules, big molecules want to be small molecules, and they want to be small molecules fast. So you can think about the process, combustion process says the big molecules in real fuels quickly pyrolyze to form small molecules, which then react by the detailed reaction mechanisms that we're building with increasing confidence, like I just showed you some. So he said, well, then we can take some liberty with these short time reactions. All we have to do is get them right. What are the pyrolysis products? What do they want to be? If we can get that right, and we can take a shortcut in modeling. And that led us to the idea that, and if we can do that, we don't have to use surrogates. Why would we use a surrogate? We just use the real fuel. So it kind of led to this idea that we can make this simplify, shorten this process. And so if you look at these classes of components of fuels, there's ranges, but here's the plot. This is the evolution over time, number of reactions and number of species. So if you kind of track this with time, people down here started, small molecule, blue that's down here. Over time, what's happening? Up here. 20,000 reactions. I mean, what does that mean? Well, so the chemists love this because they're getting closer and closer to reality. But if you're an engineer, I don't really want to have to deal with 10,000 reactions. Tell me the 100 that I need. So my colleague proposed that we produce a thing called Hi-Chem, hybrid chemistry. Hybrid meaning we would combine the detailed model that we believe in, small molecule model, which we can't change once they're measured, with a simple model, and we'll call it hybrid. Well, it wasn't immediately accepted by the community. Why? Because we were going to get swimming upstream. People were so embedded with surrogates that it was hard to, and it worked. I mean, surrogates work. You can do something with surrogates. But why not use the real fuel? So, but people wouldn't use the real fuel because it's too complicated. You have to, first of all, to run these detailed models, you have to specify the composition. So you have to go somehow figure out how to measure the composition of this jet fuel with 1,000 components. So they said, we're not doing that, we're getting a surrogate. Well, I'm a Hi-Chem person, so there may be a surrogate person out there. So there's kind of a competition how you should go about modeling real fuels. And the thing that's emerged over about 5, 6, 7 years is this Hi-Chem alternative. I'll call it alternative. And it works. Surrogate approach, okay, so again, I'll be honest, I'm biased. I think the surrogate approach is overly complicated, but it is, you could argue that it has merit, because you can say, well, we use this surrogate, then somebody else can use this, and you can compare things back and forth. If you individually go by different real fuels, you may not have the same thing. So there's something there. But the Hi-Chem approach uses real fuels, so it avoids all this question about how do you pick the surrogate? Because you might want it to match ignition delay, you might want it to match boiling point, you might want it to match so many things that, how do you even pick it? All right. So we got the Hi-Chem approach, and it was, this picture is what led Hai Wang to think about this. We showed him that we could measure multiple species versus time, and when you looked at this was heptane, I think, when you looked at it, you can kind of separate it into 2 time zones. It's logarithmic there. So in fact, a lot of stuff happens at short times. So all you really have to know is what comes out of that pyrolysis process. And it turns out, the chemists can understand this stuff, thermodynamics comes into play. Reactions always go towards what they want to be. It always goes, so if you do an equilibrium calculation, these fuels, they want to be ethylene. A lot of ethylene. So you know that that's got to be a major player. So the models were developed, and this model was that you could lump the initial phases, the initial phases of the problem you could lump it. And then you would finish up with these detailed things that we say you shouldn't change. Once they're measured, the rate constant shouldn't be changed, it shouldn't be adjusted. So that was, and heat. So the variability in this is, well, how do I represent that pyrolysis? The state of the art that he advanced was he picked 7 reactions. He picked 7 reactions, and that led to certain fragments. And let's see what have I got here. Okay, so he has a model that has 7 reactions, and there were 7 lump parameters. So basically, how much benzene do you produce, how much toluene do you produce, how much ethylene do you produce, how much methane and propane, about 7 things. And then there were some rate coefficients for some candidate reactions. And those once those are specified, you're done. Now, where do you get them? He said, well, and this is what we did a few years ago. Well, let's go do a shock tube experiment. And my colleague Tom Bowman did a flow reactor. Let's do an experiment in which we measure the time history of the real fuel and measure what comes out of the pyrolysis step. and that then is fixed. And that information would then go into the detailed model, and you would be done. We used the real fuel. We vaporized the real fuel and used it. So we measured these things. And let's see, I guess I've got an example here. Now, some of these are hard to measure. Things like propane turns out to be hard to measure, because once you get to these alkanes, these infrared spectra start overlapping so much, it really gets to be complicated. Nonetheless, we figured out how to do it. And so research evolves over time. So we started asking, well, what is the ethylene yield? The modeling says ethylene is the most important thing to get right. And so we measured, and sometimes you get 50 or 60% of the carbon will come out as ethylene. So we measured this, and it was hard. Why was it hard? Because when you get this liquid, get this jet fuel, how do you get it converted into the vapor and put it in your shock tube? You know how much you got. You put it in the heated tank, you mix it up, put it in the shock tube, some of it sticks to walls. We just had a lot of trouble learning how to control and measure that vaporization process. But it's getting better and better. So this is pretty old stuff. We're getting better. And then you say, now, in order for, let's compare this against measured flame speeds with the real fuel. Or ignition delay, and we do a lot of studies like that. And the bottom line is it works. It's a good concept. We did shell fuel, gasoline samples, we do the same thing. So whether it's gasoline or diesel fuel or jet fuel, our approach is a real fuel approach. The alternative is the surrogate approach. Two approaches, it's okay. But I'd like to talk about the hybrid approach because it's, we call this high temperature Hi-Chem. So we did this, that lumping reaction only works down to about 1100 Kelvin. When you get lower temperature, we have to bring in some other reactions. And that's kind of what we're doing now. We're doing low temperature Hi-Chem, and we're doing IR Hi-Chem. So my dream now is to say, I don't even need to do the shock tube experiment anymore. I can look at my infrared spectra, which I correlate with these products, and I can skip over to Hi-Chem. So we're now working on what I'm calling IR Hi-Chem. The spectrum alone should determine everything of the real fuel. I don't know if I've got done or not. Okay, yeah, but what we're working on now is to extend this to lower temperatures. And what we found is that whereas ethylene, methane, propene, butene, toluene, and benzene were the key products. When you go to lower temperatures, you have to worry about something new. You have to worry about some hydroperoxide species. And if you look at all that, you can decide through sensitivity analysis that we probably could get closure if we measured CO and formaldehyde. So what we're going to do is in addition to measuring the ethylene, we're going to measure CO and formaldehyde. Looks like I have some initial results here. So basically, if you, we're doing this on N-decane right now. If you do N-decane, here's the ignition delay. But when you go to low temperatures, there's two stages of ignition. So you may have heard this, at a certain temperature range, you get two stages. There's an initial stage, the fuel breaks down, and then there's a final stage. And the temperature change in that first stage and the amount, that's what you have to model. So you have to, modeling gets harder. But we now have this emerging model. It's called, there's the LLNL detailed model. So by going to a specific hydrocarbon, we can make comparisons with other models, like Lawrence Livermore. And then there's a measurement, it's the solid, and then there's the Hi-Chem. So we're now working on this problem, extending Hi-Chem to low temperatures. The concept's the same. What do you have to measure, or what do you have to predict to close the problem with a real fuel? So my argument is we're going to look at the infrared spectrum. The alternative is you take the real fuel and you measure the combustion products and patch it together with So you get the model by doing experiments with the shock tube. Okay, we're working on our Hi-Chem. Okay, I want to close up with some work on, we're always trying to measure new things. Aldehydes are important. Formaldehyde, acetaldehyde. Alkenes are important. Alkenes we measure in the infrared. Alkynes, that's 70. And one of the methods that we use is cavity-enhanced absorption spectroscopy. Here's an aldehyde diagnostic. There's a picture of formaldehyde and acetaldehyde. And we're interested in these because they are key species in this low temperature NTC regime. They're critical. If we can match that, if we measure those and match that, we're in good shape. So here's some of the problems you run into. So here's the spectrum of the ion absorption of acetaldehyde and formaldehyde, and they overlap a lot. So there's a lot of overlapping going on. And so in the end, we've looked at both a combination of infrared and UV. You can't get away from having to do spectroscopy. Reflected shockwave experiments. Okay, right now we're using 3 colors, 2 in the infrared and 1 in the UV. And from that, we can get what we need. So here's an example. Okay. We had to calibrate our diagnostics and get their spectroscopic constants. So we did that by looking at, what's it called? It's called trioxane. So there's always these tricks. You use T-butyl hydroperoxide to get OH and use trioxane as a way to get formaldehyde. So it breaks apart and forms a specific amount. So we played with our wavelengths until we could independently measure both all these species correctly. And we check it. So we measure aldehydes, prove that we're getting the right answer, success. But that might take a year. We might spend a year, 2 years. How do you, first you find out, we need formaldehyde, we need how do you do it? It might take 2 years till you're done. We've spent a couple years on alkenes. We'd like to measure, these are all alkenes, they're C2H4, it's CXH2X. They have different spectra. Now, that's the spectra which you can look up in the literature at room temperature. But the question is, what's the spectra at 1,000 Kelvin? There is no literature. There's no literature on these things at 1,000 Kelvin. So we have to figure out a way to measure it. So we know how to heat it. How do you measure the spectrum? So we spent years, maybe 4 or 5 years, learning how to measure these high temperature spectra in order to pick the wavelengths to use in a kinetic study. And what happens when you go up in temperature, the spectra get more complicated. There's a lot more lines. And so kinetics requires spectroscopy, and spectroscopy requires the shock tube. So we did isooctane pyrolysis, detecting isobutene. So you do spectroscopy, validate the spectroscopy, do some kinetics. Okay. And what do we find? When you finally get ready to do a kinetics experiment, you find that the models that are in existence, sometimes they're pretty good. I mean, this is the Lawrence Livermore national model. Of course, they've spent tens of man years, 20s of man years, building these models. So gradually, the models get better, but they need data in order to get even better. Now, acetylene is an important one. Acetylene is a tricky one. Acetylene is small enough that it still has discrete spectra. This is what we would calculate this. And then we would pick the wavelength, and then we would go measure the cross-section. And then we'd use it to study something like propene. So we used the acetylene diagnostic. So we spent years to get the acetylene diagnostic, to use it to study propene in order to finally compare with the model. And then you find out, well, that model's pretty bad. Of course, then you find out, you better go back and check. Are we sure we measured this right? Before we tell them that they got to fix their model. Aramco came along, also a little bit off. So we need these detailed models that people have, for sure. But this is just to show you that there's a ways to go. We're now beginning to look at using these to form soot formation, but we run into problems where we wish the technique were more sensitive. How do we make, here's the technique, here's one technique for how you make it more sensitive. So you basically, you increase the path length. So instead of it being one pass across the shock tube, it's 100. And there's something called, there's a conventional multi-pass cells or Harriot cells or typical ones. So they'll bounce back and forth, but you have to go in a hole and go out a hole, and it doesn't work in a shock tube. But this works in a shock tube. So you bring light in with a laser, and it goes through a mirror that has about 99% reflection. Means 1% goes through. So 1% comes in, bounces around, 99 go back, 99 goes back. But every pass, you take some of the light out onto a detector. This way, you never have to go out a small hole. This way, you can have path length without losing while maintaining alignment. And that you have to design this these passes so that you map a ellipse like this, because you can't have the light interact with each other or you get some resonant effects. There's some challenges, but this works. So the gain depends upon the reflectivity. If the reflectivity is 0.99, it's kind of like 100 passes. And here's an example. Here's an example of CO with a peak value of only 10 ppm. And that's pretty amazing. So I'm rambling around. You know, we do spectroscopy for kinetics. To do the spectroscopy, we have to have models, and we lack the data that we need, so we have to measure it. So it's all about high temperature spectroscopy and kinetics together. What's the outcome? The outcome is we can help improve chemical models a lot. Nobody's ever done it. The detection limit was 0.3 ppm at 100 kilohertz. Amazing. And we have ideas for making it even better. Okay, I'm done. Almost on time. We have one more day. Tomorrow's all fluorescence. What's fluorescence? Absorption followed by emission. We spent 12 lectures talking about absorption spectroscopy. Fluorescence is now the use of this absorption to measure with spatial resolution. A lot of problems cannot tolerate path integrated measurements. You want to study turbulence or something, you need a new trick. And one trick is to use the light emitted after absorption. We'll do that next time. Any last questions?
How did you get that minimum detection limit? The last slide?
How did I, what?
Minimum detection limit,
How did I get the detection limit?
the 0.3 ppm, yes.
I don't remember the details, but if I just look at the noise level, 10 ppm, what do you think the noise level is on that? It's certainly less than 1. That's 10, and 1 is down here somewhere. I don't know, it's probably, I don't know, the student did that, some sort of an RMS meter. You never want to be at the detection limit. It's just a number. You don't want to be at the detection. But it's just a number. What could you detect? Well, what we can do is we can detect 10 ppm very well. You always want to be at least 10. So the specification of that detection limit is kind of a number, a guideline. It's not really yeah. Good. Any last questions? Yeah.
How robust is this separation of timescales between pyrolysis and oxidation starts to kick in? Because I imagine system dependent, you start to
Yeah, that's true. Yeah.
around.
But I think it's obviously the relative time scales of the first and the second stages does change it with the system. So it's not perfect. I'm just really getting across the concept. Actually, when we model it, we probably would blend these things together in a way that actual length of time, it's more of a concept. But we measure, there's 7 yield coefficients and there's 7 rate coefficients. Some of the rate coefficients, so we have to also build some correlations for that. I don't want to make it sound overly simple, but we go away from 10,000 reactions down to 30, 40, 50, 60. And of those, most of them are inviolate. You know, we're not playing with those, we're only playing with the first stage. Last question?
Are you able to detect most of the products of pyrolysis that you expect out of Hi-Chem approach?
Yes. So the modeling tells you what you need to do. And interestingly, ethylene is a high proportion, very high proportion, especially for the normal alkanes, it's very high proportion, 60%. Next important one is methane, usually. Next is the alkenes, propene and butene, usually.
Follow-up question to that is, like, when you have gasoline, which can be slightly different from different gas stations, do they break down into almost similar composition of small?
Yeah, the important ones are the same, but the fractions change. They change because molecular structure has changed. Yeah, good. All right, thanks for your attention, and I'll see you tomorrow.